titles. So since we are quite short in time, let's start with the first speaker, Alok Laddha from Chennai Mathematical Institute. So you have already shared your screen. So whenever you're ready, you can start, please.
Okay, thanks a lot. Thank you to Nathan and everyone else for inviting me for this conference. I think I should also apologize that my talk is a bit off the main conference theme, and I'm not going to talk about string amplitudes, but just amplitudes in massless scalar field theories, and the relationships that have been recently been discovered in the context of positive geometries and scattering amplitudes for non-supersymmetric quantum. So as I think as everyone here will know, that in last several years, the amplitude-hidron program for amplitudes has seen a really striking leap into the world of non-supersymmetric quantum field theories. And it really all started with this paper by Arkani Ahmed, by A and Yoon, who showed that in the kinematic space formed by just momenta, there exists a polytope which is called associahedron, which was discovered by Jim Stasheff many decades ago, which can be realized in such a way that there's a unique canonical form, top form associated with this polytope, and that is precisely the scattering amplitude for a class of scalar field theories, which are called bias-joint scalar phi cube theories. So a lot of these words, I hope, will become clear as we go on. In fact, in this program, amplitudes, I mean, there are many remarkable things about this program and many different perspectives that come out. Like one of the main things being that the amplitudes are really thought of as differential forms on the kinematic space as opposed to just functions of the Mandelstam variables. And locality and unitarity, which is usually a postulate in the S-matrix program, is a consequence of just the geometry of the polytope in the associahedron. And then there's also a beautiful connection of this sort of geometry of scattering amplitude with the world of CHY formula. Because CHY moduli space actually has a natural compactive Pekichen, which really is an associahedron. And there are many other beautiful results that these authors discuss that really I cannot do justice to because of lack of time. In fact, the earlier work was for tree-level amplitudes for phi cube theories, and then in recent work which came out in December last year, they extended this program to loop integrants for phi cube amplitudes. And the ABHY associahedron, which contains information about the tree-level amplitudes, ABHY being names of the 4 authors who discovered it in the kinematic space, they are really replaced by some other polytopes, which are called cluster polytopes. I mean, there are many beautiful things about this work. One of what I find remarkable is the synthesis, in the sense that this associahedra, which describe tree-level amplitude, and the cluster polytopes, which describe one loop phi cube integrand, they are all geometric realizations of some finite dimensional cluster algebras, which are known as type A and type B cluster algebras. So with these results in mind, there are these 2 questions that we would like to know an answer to in this talk. One is that if you take scattering amplitude for any, say, massless scalar field theory with a generic phi to the p interaction where p is larger than 3, then can that also be understood by the geometry of polytopes? And the second question being that as a set of poles of any endpoint amplitude for phi to the p interaction is always a subset of poles that occur for cubic interaction, is it enough to look at the geometric structures of associahedra, since associahedra contain information about all the poles of the phi cube amplitude? So let me first summarize the result, and I hope I try to explain at least some of it in the talk, rest of the talk. So what we'll show is that for all the interactions, monomial interactions, there's a really nice natural perspective provided by considering a class of quivers which are obtained by dissections of polygons. And there's a history of work behind this, but the main authors who have been doing a lot of work in this direction are the ones listed here. And actually, these dissection quivers are very simple, but they lead to answers to both of the above questions that we asked, namely that there exist convex realizations of a large class of polytopes in kinematic space, such that their canonical top forms are correspond to amplitudes for arbitrary scalar interactions. And in fact, all of these forms can be thought of as lower forms on the kinematic space associahedra that Arkani Ahmed and his collaborators discovered. And it turns out that these ideas are actually fairly robust and naturally extend even to one loop integrand. In fact, in extending these ideas to one loop phi-4 integrand with Mrunmayee, we discovered actually a new class of polytopes that haven't been really analyzed by mathematicians so far. And before going to the main part of the talk, let me put a disclaimer that we will always work with color ordered or planar amplitudes, although I will not say it explicitly. So implicitly, we will always assume that all the scalars have some color degrees of freedom, either in adjoint or bi-adjoint representation. This is simply because the amplitude-hadron ideas are perhaps best developed for planar amplitudes. Although there has been some progress in the amplitude-hadron context by Zweburn around 5 years back, and in the scalar field theory context by Arkani Ahmed, ABHY, and also by Nick. So let me now start with the main idea of the talk. So let me just set up some notation that since we are working with planar amplitudes, there are these nice variables that we can look at, which I will just call xij. I mean, these are all discussed in the ABHY paper, and it's just obtained by, if you have I less than j, they're just obtained by looking at this expression for pi to pj minus 1 square. And now let's like just a step away from the Mandelstam variables and look at a polygon, which is formed by n vertices, where the vertices are labeled in clockwise direction. And now consider the following quiver. The idea is that take any dissection of a quiver. So just for simplicity, since I'm interested in a 5-4 amplitude, we are going to look at a quadrangulation of a polygon. So here the quadrangulation is given by 1-4 and 1-6 diagonals. And this is the quiver that we look at. So all the edges of the polygon which touch these diagonals, we put a hollow vertex on them. And within each cell that is formed, we put arrows which go clockwise. That's it. That's the quiver. So, and now we look at any path along this quiver that satisfies 3 conditions. One is that it should begin and end on the edges of the polygons, and it should not span edges which are in the same cell. So, for example, a path which is say v1 tilde, v3 tilde is ruled out, and it should also not begin and end on the adjacent edges of the polygon. So, for example, the path v3 tilde, v4 tilde is also ruled out. So, 2 examples of the paths which are allowed is v1 tilde, v6 tilde, and v3 tilde, v8 tilde. Now, what we do is you can just draw a chord, like a straight chord, between all the hollow vertices which are between which paths are allowed. Say, for example, vi tilde and vj tilde, and we'll just call this chord say di0 j0 between two vertices I and j. Now, if you consider all such chords which are formed by these allowed paths, then these chords form a polytope in the following sense. So each vertex of the polytope is labeled by the maximal set of chords which don't cross each other. And so the obvious example here will be if you, for example, look at chords which are 1-4, 1-6, or for example, 1-6 and 3-6, then they will form vertex of the whatever polytope we will get. So far, it's all just combinatorics. And 2 vertices are adjacent to each other if they differ in one and only one chord. This will become clear in the next slide when I show the one polytope. And such an operation where only one chord is different is called a flip. And so the edge which connect these adjacent vertices are labeled by chords which are common to both of these vertices. So just to give an example, in this case, that the polytope that we get is a pentagon, where each vertex is labeled with a quadrangulation, and you can see that between any 2 adjacent vertices, one chord is common and the other one is different. So that the idea that, for example, if you look at the 1-4, 1-6, and 1-4, 5-8, then 1-6 flip to 5-8, and that operation is what we call flip. So far what we have are these, but this definition is very general. So we get a class of polytopes which are known as accordiahedra in the mathematics literature. And here are some main properties which will be useful for us. So for any dissection Q, we get one combinatorial polytope. And if Q is a triangulation, then the corresponding polytope is actually unique and is independent of the choice of Q. So you take one triangulation versus the other, you get the same polytope, and this is precisely the associated one. If Q is a quadrangulation, which is a sort of the main interest for us right now, is then the dimension of the polytope turns out to be n minus 4/2 if it's an n polygon that we are quadrangulating. And this is same as the number of propagators you get in any Feynman diagram with n particles which involve only 5-4 vertices. So you would think that this polytope will have something to do with the 5-4 scattering amplitude. And for a generic Q, any dissection which is neither quadrangulation or triangulation, these polytopes, I mean, they all form polytopes just by this construction I described above. They are called accordiahedra. We just denote them as ACQ. And it turns out that their combinatorics and geometric properties encode 3-level scattering amplitudes for generic massless scalar field theories, where the interactions could be any monomial interaction. So now the fact that we have this combinatorial polytope, let's try to understand how to get the amplitude from these polytopes, and we really follow, just literally follow ABH-wise ideas here. So now that we have a combinatorial polytope, this is what we do. We assign a sign to each vertex, starting with any vertex. So we start with a vertex and just put a positive sign on it, and any adjacent vertices to it should then have a negative sign. And then once we have this sign configuration fixed, then in the planar kinematic space, which was spanned by these xij variables, we define a canonical, we define a form, and this form is will have the dimension, same dimension as the dimension of the polytope. And this is the kind of the more abstract definition of this form. So we sum over all the vertices of the polytope, and if the vertex has a minus sign, then there will be a flip. And we sort of wedge product over all the xij's, all the edges which are adjacent to the vertex that we are considering. Now this form looks a bit ad hoc, but this really has quite a striking property that one can check, that for any q, that it's invariant under scaling transformation. So if you take all the xij's and just scale them by arbitrary but same function of the x variables, then this form doesn't change. If q is a triangulation, then in fact this turns out to be because triangulation, if q is a triangulation that there is only one polytope independent of what q we choose, then there's a unique projective scattering form, which was the one discussed by ABH in the context of phi cube theory. So just to give an example of what this form is, let's consider a particular quadrangulation of an hexagon. And it turns out that if we choose, so if there's an hexagon, then we need only one dissection to break it into two quadrilaterals. And then it turns out that if you choose references, for example, 1, 4, and you follow this formula, then for each choice of a reference, whether 1, 4, 2, 5, or 3, 6, you get like these three possible forms with a relative minus sign between the two vertices of the polytope. So each vertex here is one dimensional, where the vertex is either labeled by 1, 4 dissection and 3, 6, or 2, 5 and 1, 4, or 3, 6 and 2, 5. So we really have three distinct projective forms for one for each choice of q. Now it turns out, okay, but this form so far have really nothing to do with the amplitudes of the theory, but it turns out that the same quiver that we looked at, we can use it to embed these combinatorial polytopes into the kinematic space, and that is the sort of the heart of the procedure. So I won't be able to go into too much detail, but the idea is that these quivers and the paths paths that construct this quiver, they generate an algebra. And so you just take basically algebra generated by all the paths which constitute the quiver, and you quotient out by paths of length 2 which belong to the same cell. So so then you get an algebra which is called the gentle algebra. And it turns out that for any q, whether it's a triangulation or quadrangulation, this algebra can be defined directly to generate a set of constraints which locate this combinatorial polytope into the positive region of kinematic space. So this really is a remarkable, I think, result that we can do it for any of these combinatorial polytopes. So we always get a nice convex embedding into the kinematic space. So just to give you what these constraints are, which come from this algebraic perspective, let me just remind you that the standard Mandelstam variables Sij are linear combination of these planar variables that we defined earlier. And it turns out that if suppose your dissection was a triangulation, let's just call it T, then it turns out that these constraints are very, very easy to define. So consider TC to be the triangulation which is obtained by rotating T counterclockwise. Then these constraints are simply given by fixing all these Sij's which are not in TC toCij's. And we have to do it only for I and j which differ by at least 2. So this is the class of constraints, that one just directly generates. Intuitively, these constraints can be understood as saying that they really freeze all the Mandelstam variables which will never occur as pole in the phi cube amplitude, because of the fact that I minus j is greater than 2, and we are looking at planar amplitudes. Just by playing with some examples, you can check that this freezes all the Sij's which will never occur in the propagator of the phi cube amplitude. And now this was for the realization of the associahedron into the kinematic space, and so we don't get one realization, we get many realizations. You could have started with any triangulation. So although combinatorially there is a unique polytope, you have many different realizations in the kinematic space, in the positive region of the kinematic space. But now suppose Q is not a triangulation but a quadrangulation, then then also it's very easy to understand what the polytope realization will be. And the idea is that it's very simple. Basically, take any triangulation which encompasses the quadrangulation. So you just take your quadrangulation and fill the polygon with some dissections which complete it into a triangulation. And the idea is that we take these constraints which are defined in 4 and we append them with the constraints which are defined in 5, where we just fix xij's to constants where all the ij's are in the new dissection that we added in the triangulation. And again, intuitively, you can actually, if you stare at it, you can convince yourself that these extra constraints really freeze all the propagators that are in the cubic channels, but which will never occur in a quartic Feynman diagram. So now with this we get a convex realization of this combinatorial polytopes in kinematic space, and there are some nice properties that we can immediately see, that namely that for every triangulation of an n-gon, we get distinct convex realization, as I discussed earlier, and a large class of these were discovered by Nima and his collaborators, as well as by mathematicians Yu Thomas and Bezier Math et al. The realizations that they discussed, which are known as ABHY associahedra, they come from a cluster algebra perspective, but the ones that you get from this dissection language are more general. I mean, you get all the ABHY, but you get a lot more. And if Q is a quadrangulation, then the convex realization is a polytope which, modulo some technical conditions that we discuss in our paper, you can always show that you can always embed it in one of these associahedra, which I just call AT, as long as the dissection Q that you start with is contained in some triangulation. And in some sense, the last property shows why associahedra are like the master polytopes from physics perspective, because all the other accordiahedra can always be embedded in them. And now with all this machinery, we can now try to answer our questions that can we understand the amplitude for say phi-4 theory in terms of the polytopes. So sorry, how much time I have, Carlo? Hello? Hello?
Great. So you have 8 minutes.
I have 8 minutes.
Yes.
Oh, okay. Thank you. Yeah. Okay. Maybe I yeah, just maybe I will just keep this. Let me just say that let me just give you the main results, and I go to some work about phi cube, the one loop amplitude, which is maybe more interesting. So it turns out that with all the machinery we have built, we can actually show that. So this is something that we discussed, that there is a set of projective planar scattering forms in the kinematic space for any phi to the p interaction. For p equal to 3, where we have cubic interaction, this form is unique, but for p greater than 3, we get a whole set of these forms which are parameterized by these dissections Q. And it turns out that this is something I didn't get time to discuss in detail, but it turns out that when we take these forms and we just restrict them for any Q to the associahedra, then we get lower forms, and these lower forms have simple poles on the faces of the associahedra, which correspond to the phi to the p vertices. I mean the singularities which occur in Feynman diagram for phi to the p interaction. And in fact, more is true, that since each such form is a canonical top form on a convex polytope called accordiahedra, which is also realized in kinematic space, and this accordiahedra can always be realized inside the associahedra in the kinematic space. And locality and unitarity emerge just due to some really striking properties for any of these accordiahedra, which is such that if you take any face of any accordiahedra, it always breaks up into products of lower dimensional accordiahedra of the same family. So you start with the accordiahedra coming from a quadrangulation, its face will never be something which will come from a accordiahedra which comes from pentagulations, for example. Okay, so now in the remaining time, let me just quickly tell you how these ideas generalize very nicely to one loop integrand for quartic interaction. This is some work in progress with Brunmai. So again, in a recent work, Arkani Ahmed and his collaborators showed how to get one loop phi cube integrands. And the striking aspect of their work was that they had they synthesized everything in the language of cluster algebras, in the sense that the polytopes for the tree level amplitude are associahedra, which come from type A cluster algebra, and the polytopes for the one loop integrands are these polytopes which are realization of so-called type D cluster algebras. So again, we want to ask this a similar kind of question we asked before, that is there a generalization of this class of polytopes accordiahedra which gave us the tree level amplitude for phi-4 theory, for example, that give us a one loop integrand. And just as in the case of the tree level amplitude, where you could understand the forms for the phi to the p theories as lower forms on the associator is the same true in the sense that we have some lower forms on the type D polytope, which give us a scattering amplitude for integrand for phi 4 one theory. So let me just quickly tell you what the basic idea is. So combinatorially associator is, as we know, now determined by triangulation. It turns oh, thank you. It turns out that we can ask that is there a nice such combinatorial model for the type D polytope, which is in some sense simpler to understand than the cluster algebra language, and there is indeed a model which is also based on dissection, and this was a model discussed by Ceballos and Pilot some years ago. So here the idea is that instead of triangulation, we consider what are known as pseudo triangulations, which is a pseudo triangle is basically any polygon which has precisely 3 convex corners. So just to give you an idea, this is a centrally symmetric pseudo triangulation of a polygon which has an annulus in between. So as you can see that it breaks the polygon into cells which are either triangles or pseudo triangles. So V1 is a triangle and V2 is a pseudo triangle. And now it turns out that all the dissections of these centrally symmetric pseudo triangulations actually give you the same the variables which occur in the phi cube one loop amplitude integrand. So for n equal to 3, if you just look at all these labels, so for example, look at a label which is going from 1 to 3, and you look at a label which is going from 1 to 1 bar on the right and 1 to 1 bar on the left, they all, and you can also have, for example, a label which is going from 2 bar to 1, which I haven't drawn here, but you could just draw a chord here. All of them label the variables which will occur in a phi cube integrand. So, and here the interesting variables are these y's, which kind of parameterize the loop momenta, which occur in the integrand. And now it turns out that the same procedure that we had done before actually works in the sense that I don't have time, so I will just rush through it. That if you start with any dissection quiver for any of the pseudo triangulation, then you can follow the procedure that we had followed earlier and get a wide class of convex realizations of the type D cluster polytopes. There was one discovered by Nima and Song and others, but you can get a wide variety of them. And again, the same is true. The idea is exactly the same, that you really have to basically do some diagram chased in and write the constraints carefully. If you follow the same procedure that you have for the pseudo triangulation for pseudo quadrangulation, you have a nice picture that you get a new class of polytopes. Sorry, because of lack of time, I will skip that. Whose vertices are really labeled by all singularities of the Feynman diagrams of the 1 loop phi 4 integrand. So these polytopes, I mean, their convex realizations in momentum space can be understood very nicely because we just write constraints and solve for them. But it turns out combinatorially they have not been explored yet by mathematicians. So and the reason is the following. That so I just maybe end with this one, that there is nice algebraic connection for all the polytopes that we have found so far in physics. So the associahedra are related to type A cluster algebra, or this algebra coming from the dissections that we discussed here. And the accordiahedra also comes from dissections which are not triangulation. Type D cluster polytope come from type D cluster algebra, but the polytopes that we are finding now, it is not clear if there is a direct relation with any of the algebras which are discussed so far in the literature. And although we focused on the quartic interaction at one loop, simply because our ideas really just rely on any dissection, we think that it can be worked out for any monomial interaction. And so that's basically the idea, that these ideas of dissection quivers and accordiahedra and these path algebras, which are called Divergent, they really offer a unifying perspective on how to understand scattering amplitudes and integrands in terms of positive geometries. There are other interesting questions, connection with the CHY moduli space and binary geometries, which have been discussed recently. And just a special thanks to Vincent for many discussions on the very complicated math literature, and thank you all for listening. Sorry if I went over time.
Okay, so thanks. In fact, you have still 1 minute if you want.
Oh. Okay.
But if you feel that you have conveyed your message, then we can finish here. We can thank Alok for his very nice talk. And so we have some time for questions now. So please either raise your hand or write on the chat. And okay, so Jim wants to ask some question. Hello.
Yes. Do you have any pictures of the 3-dimensional polytopes other than the associahedra, for which there are a lot,
Yeah, I think for the accordiahedra, at least for the what are known as the Stokes polytopes, which come from quadrangulation, there have been some pictures that people have drawn.
Good.
Yeah.
Two sources of excellent pictures. I don't know if it includes the associahedra, are due to Satyan Devados and
Yes, exactly. Yeah, right.
okay, you know it
Yes,
well then,
yeah.
and also Stefan Forsi. I'll send a chat note to everybody since you probably can't decipher those names unless you know them. Very, very interesting to me, of course. And to think my thesis was of no interest other than to itself. Thank you.
Thank you.
Okay, so as I said, if you want to ask questions, you can easily share. I mean, you can easily raise your hand from the chat, or you can write also on the chat some message.
Hi, can I ask something?
Please.
So you said that these 5p accordiahedra are embedded in some way in the master associahedron, the 5 cubed associahedron. Am I
Yeah,
right?
we can always ensure that we can always ensure that happens. I mean, there are some technical conditions, but
I see.
Yeah,
So
we can
can
show
you can you also see this as some sort of a hierarchical embedding, like 5p plus 1 embedded in the 5p accordiahedra and things like going up like that?
Yeah, we haven't looked at it, but yeah, I would think so. that should work.
Okay.
Okay. So I don't see other requests for questions. So we may still leave. So we still have a few minutes in principle, but we can also. So I can hear someone has talked.
Yeah, I have one question.
Okay, please go ahead.
Alok, if you could comment on this thing you said that you said there's some connection with the forms in the CHY moduli space from
Yes.
the construction you have. Could you
Yes.
comment on that a bit?
Yeah, so actually, as I was discussing that for example, you can think of the 5-4 amplitudes as coming from lower forms on the associahedra, and this kinematic space associahedra is actually diffeomorphic to the compactification of CHY moduli space, which is also an associahedra. So the natural question to ask is that are there any, and this diffeomorphism is really given by the CHY scattering equation. So then the question to ask is that are there any lower forms on the CHY moduli space whose push forward under scattering equations produce precisely these lower forms on the associahedra. And we found we found such forms that, I mean, they look a bit ugly, but that they exist, that there are these lower forms on the CHY moduli space. I mean, the interesting sort of puzzle even which probably even exists now is that from the CHY perspective, for any theory, one always looks at top form. So even the 5-4 CHY integrand is really like a top form, but the form is different. So there the polytope is not changing in some sense, always the worldsheet associahedron, but one changes the forms. But here in the positive geometry picture, it looks like one changes the polytope, or one changes one really changes the lower, when it goes to lower and lower forms. It is not entirely clear to me that what's the best way to understand these connections for generic theories. I mean, we think there are lower forms on the CHY moduli space, but we don't know if they don't look very, they look a bit complicated. Yeah.
So am I to understand that going to lower forms is in some sense sort of looking at sort of making going to like smaller number of, I mean, if you had it's like going to cubic interactions, right? Like going to lower and lower forms, like trying to express everything.
No, going to higher interactions actually, because the lower forms will have less number of poles, and so they will correspond to higher interactions. They will not explore all the poles of the phi cube theory, the phi cube diagram.
Ah, okay.
Yeah.
Okay, so I think we can also postpone some more questions for the discussion session after all the other talks. So I think now it's perhaps time to thanks again Ladd and Alok, and to introduce the next speaker, who is Oliver Schotterer from Uppsala University. So Oliver, are you there?
Hello.
Hi, Ollie.
Can you hear me?
And I can hear you. So you can start sharing your screen. I can also see you. Hi. And so you should be able to share your screen. Just okay. So
I was interrupted, says my computer.
Okay, so we cannot see your screen. At least I cannot see it.
Right. Let me try again. Okay, I'm sorry. Maybe it's something about the PDF viewer. Let me try it again. Share screen. Here it could be. Is it better now?
So now something is working.
I
think we are on the right track. Okay.
Good.
Okay, so welcome to Oliver, who is going to tell us about towards basis of worldsheet integrals for string amplitudes. Please go ahead.
Yeah, thanks a lot, Carlo, for the kind introduction, and thanks to all the organizers for inviting me to speak. So this talk is motivated by some recent papers with my collaborators Carlos Mafra from Southampton, as well as Jan Gelken and Axel Kleinschmidt from Potsdam. We wrote these papers about the worldsheet integrals that you find in one-loop scattering amplitudes of various string theories. 2 papers with Carlos on the open string integrals over worldsheets of cylinder and Möbius strip topology. 2 papers on the worldsheets of torus topology. And as I started to prepare, I realized that I should spend less time on the results in these papers, but to, well, actually spend the bulk of the talk on the background, on the philosophy, on the kind of organizing principle of scattering amplitudes and string theories that worked pretty well at 3 level and 1 loop, and partially we have seen it working at 2 loops as well. Okay, so this will be about explaining an approach to scattering amplitudes, which has somewhat a flair of doing linear algebra on the worldsheet integrals. That's why the title. Whoops. So now in the best case scenario, I can switch slides. Oh yes, I can. Good. So let's start with the usual textbook picture, how to think of string perturbation theory. As you look, for instance, at a closed string scattering amplitude, there are different perturbative contributions coming from worldsheets of different genera. I think you all know this pretty well. And now what's the mathematical expression associated to a given worldsheet topology? So here is the cartoon that I want to draw for these tree level and loop level closed string amplitudes. There are 2 steps to obtaining the mathematical expressions. Step number 1 is do some CFT, compute a correlation function of vertex operators drawn in blue. And depending on the formalism you use, there are different flavors of BGOs, picture changing operators, regulators, and all that. And as you can already see from this blurry statement about the green stuff, I try to not commit to a specific formulation, whether we do pure spinors or RNS. Okay, so once you're done with part 1, compute a correlation function on a given Riemann surface sigma g, then it's time to integrate. Namely, you're supposed to integrate over the moduli space of this n-punctured surface, like integrating essentially over the punctures of the vertex operator insertions and over the moduli of the surface. And of course, in RNS, we know that there's in fact about supermoduli. And as we all know, there are issues at higher loop orders with the non-splitness of supermoduli space. And I will maybe get back towards the end of this disclaimer, but most of my specific claims at this talk are at genus 0 and 1, where we are well in business in getting rid of the supermoduli. So I hope nobody will get nervous if I suppress the word super in many of the next slides. Okay, so now what's the mindset or organizing principle to be proposed here? well, we want to scatter vectors or higher spin particles. There will be a lot of dependence on polarization, degrees of freedom, and momentum. So there's a hell lot of tensor structure in these vertex operators, and all these polarization tensors don't depend on the moduli. So of course we should pull them out of the integral. And the question is now, once you have pulled out a few polarizations out of the integral, what is left to do? How many functions of the z's and tau do you have to integrate over? Maybe we want to be economical. Maybe we want to reduce the number of independent integrals to be performed. And in particular, when it comes to evaluating or low energy expanding the integrals, we want to be first economic, but also it turns out that there are a lot of benefits to generating alpha prime expansions if you're in good control over a basis at a given loop order at a given number of external legs. So let me give a super simple illustration of this program. Let's look at genus 0 for 4 gravitons, 4 massless closed string excitations. So when you compute the genus 0 correlator of these 4 vertex operators, then you will find that all the tensor structure can be nicely packaged into the supergravity tree. So this you may express in terms of the famous TA tensor contracting linearized Riemann curvature, or you use your favorite superspace to go for the supersymmetrized version. So we have pulled out all the TA tensors, all the supergravity trees out of the integral. And what is left to do is integrate over one puncture on the Riemann sphere. And this is an integral which we know how to do since the days of Virasoro-Shapiro. So this is the one-dimensional basis of 4-point closed string amplitudes at tree level. And one way of seeing that this is a basis, maybe you could have imagined different denominators in that second line, whether there's 1 over z bar or 1 over z. But no matter what I do, I can go back and forth by using cheap gamma function identities. So this is a very explicit way of seeing that the integral basis here is one-dimensional. And to already give one spoiler right here, if we were to repeat this for n gravitons rather than 4 of them at tree level, then there would be a much larger basis that both for the holomorphic and anti-holomorphic dependencies, there is a basis of n-3 factorial integrands. So the overall basis of sphere integrals is n-3 factorial squared. More details to be given later. Okay, so this is the kind of mindset I want to run, not only at tree level, but specifically at one loop, along with some wishful thinking that there may be some partial results along these lines at 2 loops, and maybe a bit beyond. So let me repeat. The idea is that all the tensor structures seen in a string amplitude generated from the vertex operators will be separated from the integrals over worldsheet moduli. So let's use capital K as a collective notation for the polarization packages. And let's use here this I for the basis integrals, which no longer depend on polarizations, but where you do find a lot of alpha prime dependence. And all the leftover alpha prime dependence, as exemplified by Virasoro-Shapiro, it comes from the dimensionless Mandelstam invariance. With SPQ, I am absorbing an alpha prime into the momentum dot products, the Mandelstam invariance where the amplitudes have poles and branch cuts. Now, what's the benefit of organizing string amplitudes like that? So there's a multitude of motivation lines. Let me give a flavor of 3 of them. So for instance, if you want to learn about field theory, or if you want to learn why gravity is perturbatively a bit like the square of gauge theory building blocks, if you say you want to understand the Bern-Carrasco-Johansson duality or double copy of gauge theory and gravity, then you want to do the alpha prime to 0 limit of string amplitudes. And this is so much smoother if you are on an integral basis. Like the first construction of BCJ numerators was based on being a tree-level basis of Park-Taylor integrals. So it plays a big role for doing efficient field theory calculations to have a basis of integrals. But also for string theory per se, one motivation to compute string amplitudes is to learn about string dualities, to have some testing grounds or even smoking guns for new duality phenomena. So specifically, S-duality of type 2B superstrings can be nicely understood at a perturbative level if you know how to do alpha prime expansions of tree-level 1-loop and higher loop amplitudes. And the biggest S-duality lessons come from comparing different loop orders. And you want to make sure that there are the same kinematic factors, the same tensor structures going on at different loop orders to make sure you can compare them or that you can read off the fingerprints of S-duality. So this is one of the reasons why it's very important to have an integral basis, that you see what's going on in the kinematic coefficients. And then there's a math motivation. Not sure whether I can detail that, but having an integral basis is quite essential to performing the alpha prime expansion and to see what kind of periods appear there, like multiple zeta values, polylogs, modular form, and many more. So this is a topic with very rich cross-fertilization with number theory and algebraic geometry. And let's say the physics input we can give becomes enhanced once we are in the possession of integral basis. All right, this is the motivation. Let me now get a little bit closer to what kind of integrals and integrands I want to look at. So as I said, we start by evaluating CFT correlators, and there is an evergreen piece of every correlation function coming from the plane wave parts of the vertex operators. So no matter which state we scatter, there will be an e to the ikx in the vertex operators that give rise to the so-called Kober-Nielsen factor, to be denoted by kn. So this is an exponential involving all the Green's functions connecting pairs of external states. So we sum over all pairs I and j, and we need to tailor the Green's function to the surface we are on. Like there will be a log at tree level and some theta functions at loop level. So we can be sure that for any massless or massive scattering amplitude, we will have that Kober-Nielsen factor in the integrand. But this is not the end of the rope. If you do something non-tachyonic, there will be some polarizations in the vertex operators, contracting fields with vector index like the del z in case of gluons and gravitons. So there's something less universal besides the Kober-Nielsen factor. And this all boils down to doing OPEs, where you extract simple and double poles in the punctures, more precisely in the differences Zij of the pairs of punctures. Okay, so we need to deal with the patterns of Zij's that we generate from iterated OPEs. So this is maybe the more stressful part of doing the integral reduction. So you have to do a lot of OPEs, and then it remains to check how many of these OPE channels are actually independent. And by independent, I mean, let's mod out by algebraic relations, such as partial fraction, but let's more importantly, mod out by total derivative relations. Let's make use of the fact that the Kober-Nielsen factor flattens out boundary terms in the punctures. That's not true for the moduli tau, and there might also be subtleties for supermoduli, but for total derivatives in punctures at low loop order, no problem, all the boundary terms are gone. And maybe you can see here in the fine print that I'm not even committing to open or closed strings here. So no matter whether you do an open string insertion on the boundary of the world sheet, or whether you do a closed string insertion of the bulk, you can throw away all the boundary terms, all the total derivatives in the punctures. So modding out by all these relations here, the leftover space of possible integrands, it can be viewed as a cohomology. More precisely, a twisted cohomology with a twist introduced by this Kober-Nielsen factor that heavily influences what the shape of the total derivatives is from these derivatives of the Green's functions. So I assume you heard a lot of this in Eduardo Casali's talk. I think he can give a much cleaner account on how to connect it with the math literature on twisted de Rham theory. Yeah, so this is the kind of integral reduction I have in mind at the integrand level. But let's also talk a little bit about integration domains, which become pressing when you do open strings rather than closed strings. Because whenever you have an open string insertion of the boundary of a surface, then you need to commit to the cyclic ordering in which you place your vertex operators there. And the main purpose of the slide is to introduce the notation cap m little gamma. So whenever I write down a little gamma, then I refer to an integration domain for open strings with the info of the cyclic ordering in which the punctures are sitting on the worldsheet boundary. So having said that, you can view the integrals in open string amplitudes as pairings between cycles and integrands. So let's call these integrands cocycles, more precisely twisted cocycles, since there's a Kober-Nielsen factor around to influence your integration by parts relations. So you can think of an open string integral, no matter which loop order, as a pairing between a cycle and a cocycle. And fortunately, we have heard a lot from Eduardo yesterday, how you can find relations between different choices of the cycle. So to make my life easy, I will treat the cycle as a spectator in the rest of the talk and tell you more about the cocycle side of the story. I will be talking about the relations taking place of the co-cycle side. And these are manipulations that are completely independent on the way how Eduardo uses string monodromies to reduce the cycles. And specifically, if time allows, I will hopefully arrive at an explicit account on the basis of co-cycles that I would recommend at tree level and one loop. Now, given that open string amplitudes are here presented as a pairing of cycles and co-cycles, what's the closed string counterpart of that? Well, for closed strings, there is no notion of cyclic ordering. All the vertex operators are somewhere in the bulk of the world sheet. So let's forget about the cycle information. But the extra structure of the closed string is the distinction between Z and Z bar. So now I can write down a co-cycle for both the meromorphic dependence and for the anti-meromorphic one. I could make a small technical footnote that things are not quite meromorphic at genus 1, but nevertheless, if you use chiral splitting, then this is an exact statement that closed string integrands factorize into a meromorphic and anti-meromorphic part. So once you have done your homework for the open string to figure out a good basis of co-cycles, then the closed string will just take a double copy of that. One, the original co-cycle with Z arguments, and then its complex conjugate. And needless to say that you can freely choose different basis elements of the co-cycles, phi I and phi j, for the meromorphic and anti-meromorphic side, respectively. Yeah, so as I said, I will be describing some explicit basis choices for these co-cycles phi at tree level and genus 1. And let me emphasize that these bases are meant to be universal, namely applying to various perturbative string theories. That it should hopefully be the same basis, no matter whether I am in the supersymmetric type 2 theory, or let's say in a non-supersymmetric bosonic string theory. And the slightly more speculative part is, let's also try to be universal with respect to the external states. I mean, even though most of the examples we know are about massive states, there will be mathematical, not massless states, there are mathematical arguments, or at least smoking guns, that the same integral basis can be recycled to combinations of massive states in the external legs. So I'm looking forward to Jacobati's talk on massive scattering amplitudes. All right, having spent a lot of time on the general framework, let's now go more specifically to genus 0 and genus 1. Let's start at tree level, where the basis decomposition is rigorous and, let's say, underpinned by mathematical theorems. So if you do tree level scattering of strings, if you put, say, open string punctures on the boundary of the disk, then you will encounter, first of all, the Kober-Nielsen factor as a universal piece, and then the OPEs among the vertex operators that can be organized to give you simple poles that are collected in so-called Park-Taylor factors. So this funny notation PT for Park-Taylor, this refers to a collection of simple poles in punctures Zi minus Zi plus 1. And let me emphasize that this notion of cyclic ordering in the Park-Taylor factor does not need to be correlated with your integration domain. So that's why I'm giving these disk integrals Z two entries. The first, the gamma, refers to a cycle. Let's keep it as a spectator. And at a fixed cycle, you can put the Park-Taylor integrands in various cyclic orderings and study the relation between them. Relations with respect to partial fraction, but more importantly, with respect to integration by parts. So if you patiently express Kober-Nielsen derivatives in terms of Park-Taylor factors, you will arrive at a huge equation system that allows for a reduction to very few of them, namely only n-3 factorial. This is far less than there are cyclic orderings of the external legs inside the Park-Taylor factor. Okay, and let's say the mathematical framework has been investigated already in the 80s by Aomoto, so it's really at the level of a theorem that Park-Taylor factors have an n-3 factorial basis that you may, for instance, index by permutations rho of your favorite group of n-3 legs. But of course, everybody is free to use his or her favorite basis. Yeah, and it's a pity that this math theorem came to the attention of the string amplitudes community quite late. So I'm still grateful to Sebastian Misera for bringing this to my attention. All right, so this is the basis of disk integrals that I want to use for open string tree level amplitudes. Pick your favorite collection of n-3 factorial Park-Taylors. And let's now see how this basis decomposition looks like, either in superstrings or in open bosonic strings. So let's start with a supersymmetric example where this integral reduction was firstly carried out explicitly. Together with Carlos Mafra and Stefan Stieberger, we used the pure spinor formalism to simplify the endpoint function at tree level of the gauge supermultiplet. And it was a big blessing to have the manifest supersymmetry and the BRST invariance of the pure spinor formalism, because this nicely guided our quest for reducing the integrals to smaller and smaller collections until we finally arrived at an n-3 factorial basis of such Park-Taylor integrals. And now that you're in a basis of integrals, it's not surprising that the kinematics will be manifestly gauge invariant and supersymmetric. And to our delight, it could be assembled to tree-level amplitudes in super Yang-Mills field theory. So all the polarizations are sitting here in these color-ordered super Yang-Mills trees. That's the reward for going in a basis. And if you are curious about the exact composition of Yang-Mills trees and Park-Taylor integrals, here's a matrix S, which you may know from the Cavalier-Valentine relation in supergravity. So this is some polynomial in the Mandelstam variables whose details are not important here. Let me just say it's a field theory quantity that you can look up in the KLT formula for supergravity. So in short, the open superstring, when written in an integral basis, is a superposition of super Yang-Mills trees taking care of polarizations. And all the alpha primes are in scalar integrals, the Z trees. So you don't need to worry about polarizations anymore as you evaluate or alpha prime expand these disk integrals Z tree. Okay, now given that this worked so nicely for the superstring, let's repeat the integral reduction for the bosonic string. Here the calculation is in practice more challenging, less supersymmetry on our side, but you can still do it if you're brave enough to torture Mathematica with its integral reduction. But now the kinematic coefficients that we find, they start to depend on alpha prime and be different packages of the polarizations. And in fact, even for the bosonic string, there's a field theory interpretation. It's not just Yang-Mills color-ordered trees, but some augmentation of Yang-Mills by dimension 6 operators. Quite an amusing gauge theory, which introduces alpha prime dependence. And this is something that Henrik Johansson and Josh Nola have firstly constructed in the study of conformal supergravity. And I guess Renan will tell us more about these. Good, so these were two showcases of how integral reduction pays off for the open string at tree level. And needless to say, this result has an echo for the closed string at tree level. As I said before, the closed string gives you the option to combine meromorphic with anti-meromorphic co-cycles. So for each Park-Taylor, there's also a complex conjugate friend, Park-Taylor bar, which you can put in a different cyclic ordering. But there's no more information about an integration cycle. So that's why the first slot of the sphere integrals W, the first slot is dedicated now to anti-meromorphic co-cycles rather than a cycle. Okay, and you can again ask about the kinematic coefficients, and they are worked out in detail at tree level. It's bilinears, either in Yang-Mills trees, or if you do some tourism across the perturbative string theories, you can trade some of the Yang-Mills factors by the less non-supersymmetric df square plus Yang-Mills kinematic factors. So that's the picture at tree level. And now the rest of the talk, I want to give you a flavor of some recent results at the one loop level, where the initial question was, what's the analog of the Park-Taylor factors as you move away from tree level and approach genus 1? What is the replacement of these simple poles in the punctures collected by Park-Taylors? What kind of functions on a torus do I need to place on their behalf? So I will now tell you about certain integral basis or conjectural integral basis at genus 1 on a torus worldsheet or a cylinder worldsheet, where the Kober-Nielsen factor is augmented by some universal collection of co-cycles to be denoted by phi here. And I will specify the combinations of theta functions that go in here. And to your amusement, there will be some extra bookkeeping variables, ADA, that don't have a tree level analog. And also, I have not yet integrated over the modular parameter tau. That's left for later. So let's leave the modular parameter tau as a spectator for the moment. It will sit in the theta functions. So when you contemplate what could be the one-loop analog of a Park-Taylor factor, you can check what kind of nice properties there are for Park-Taylors and what one can do to uplift them for genus 1. So for instance, there are partial fraction relations among the simple poles in Park-Taylors. And wouldn't it be nice if we could preserve these partial fraction relations at genus 1? And now the rule of thumb to uplift a simple pole to genus 1 is to use an odd theta function, or more precisely the logarithmic derivative, d log theta 1. Well, that's the rule of thumb to do the Wick contractions on a genus 1 CFT calculation. But now the partial fraction no longer works. This d log theta 1 has some global properties dictated by the modular parameters tau that simply crash your partial fraction. So this is a bad signal if you want to do integral reduction. So let's try to find something better, which is closer to satisfying partial fraction. And the answer to this is a funny combination of theta functions that goes by the name of the Kronecker-Eisenstein series. So I guess the details are not so important, but what matters is there is a way to uplift the partial fraction relations to some combination of theta functions that are doubly periodic on the torus, as they should, but the price to pay for the uplift of partial fraction is some extra variable eta. Okay, what's going on with eta? So this is a bookkeeping variable, and the tentative genus 1 basis that I want to flash, well, it's generating series with respect to eta, a generating series of integrals that appear in the actual string amplitudes. So the conjectural genus 1 basis goes as follows. Combine the Kober-Nielsen factor, the evergreen as before, with certain products of Kronecker-Eisenstein series. So in the same way as the Park-Taylor factor is a combination of many simple poles, you should view the Kronecker-Eisenstein series as the atom of a basis co-cycle. And to form a molecule, you take a product of several Kronecker-Eisenstein series. So this phi is just a product that has a resemblance to the Park-Taylor factors. So
Oliver, at the moment you are during your question time. So just to tell you, so you're eating your question time.
Okay, so let me make it a short meal. So just one and two examples on how these generating series compare to actual string amplitudes. The simplest one loop amplitude, we probably all know, is the monumental Green-Schwarz calculation in '85, where they computed the 4-point graviton amplitude for the type 2b superstrings and type 2a. And the maximally supersymmetric result is quite simple. It's just the Kober-Nielsen factor and nothing else in this massless 4-point amplitude. So this is the virtue of the supersymmetry, the type 2b theory. And at the level of this generating series, it simply means pick the poles in eta and forget about all the higher order terms in eta. But here is one showcase why this is a universal basis. If you want to do the bosonic string instead, there are some derivatives of Green's functions from the OPE, and this simply means you need to go deeper in the eta expansion of the putative integral basis. So that's one instance why we claim that this is a universal integral basis. The eta variable is your friend to flexibly switch from more supersymmetric theories to less supersymmetric theories. Okay, to leave some time for open questions, let me wrap up. I was advocating an organization of string amplitudes where you use integration by parts on the worldsheet to go to as few co-cycle factors, to as few functions of the moduli and supermoduli as possible, which at tree level brought us to a basis of Park-Taylor factors, and which at one loop brought us to a combination of theta functions known under the name Kronecker-Eisenstein series. And given that this is a generating function, maybe this is also having something to say on massive state amplitudes. So I was encouraged to this scenario by correspondence with Albert Schwarz, who is giving a talk later this afternoon. All of this program has been carried out up to including genus 1 so far. It remains to see how successful we are at higher genus and how we deal with the non-splitness of supermoduli space. And having these integral bases for conventional strings. That's with alpha prime. There's also a lot of spin-off for the ambitwistor strings that we will learn about in tomorrow's talk by Lionel Mason and Yvonne Geyer. Good, so this brings me to the end. Thank you very much for your attention. And sorry for going over time.
So thanks, Oliver, for the very nice talk. I think we have time for one question maybe, but then remember that we can always postpone questions for the discussion session after the talks. So if there is some quick question now, please go ahead. I'm not sure I see raised hands, but perhaps it's just that I'm not able to see them, because even before there was someone talking and I was not seeing him. Okay.
Hi.
Okay, so there is some question. Please go ahead.
Yeah, Oliver, can you tell me, is there any general result for how many independent such bases will be at genus G? For instance, for tree you have n-3, and for genus 1 you have n-1 factorial. Is there some general argument which says how many should be at, say, any arbitrary genus?
Mm-hmm. Okay, so let me start by going to our claim for genus 1. So for these Kronecker-Eisenstein integrals, we believe that the number of independent permutations is n-1 factorial. That's the statement for the co-cycle side. But your question was probably on the cycle side, the homology rather than cohomology. Is that right?
Yeah. Yeah.
So I think about this, we heard something by Eduardo Casali yesterday, where there are these loop level monodromy relations that relate different cycles. And let's say for the higher genus version, I guess there's more combinatorics going on. Is it true, Eduardo, that it was still expressible through factorials, the number of independent cycles under monodromy relations? Okay.
Yeah, Piotr speaking. Something like that, yeah.
Okay, thank you, Piotr. And yeah, I think also Albert Schwarz and Dmitry Fuchs had some ideas. I think they have some topological arguments to do the counting at higher genus. And I vaguely remember also seeing some factorials of genus and n-dependent numbers.
Okay, thanks.
Okay, so I think we can postpone more questions for the discussion session later. So since we are very strict in times, we can thank again Oliver for his very nice talk. And so next speaker is Leonardo Rastelli. Hi, Leonardo.
Hello, can you hear me?
I can, yes, I can already see your screen. So I think it's okay. So Leonardo is going to tell us about maximally supersymmetric RG flows in 4-dimension and integrability. So Leonardo, please go ahead.
Thank you very much. I'd like to thank the organizers for inviting me to give this talk. They insisted I should give it, although as you shall see, the relation with string field theory is non-existent or perhaps very loose in the motivation. So the audience would be welcome to take a break if they're not interested in the subject, which is rather far afield really from the rest of the workshop. So this is work that has been in progress really for several years, and finally we were put out our paper last Monday in collaboration with wonderful collaborators, João Caetano and Volker Pellarts. So the subject is something a little exotic, but not as exotic today as it used to be a few years ago, which is whether we can interpret in some field theoretic terms the operation of going against the RG flow. So as we are familiar, if we have RG flows between two fixed points, near the infrared fixed point, we can describe the theory in terms of the infrared conformal field theory perturbed by a leading and then a whole sequence, infinite tower in general, of higher dimensional irrelevant operators. And unless you have some principle, for example, you know exactly the flow or some other idea that allow you to fill in the dots, in general, of course, it's an ambiguous operation to go against the RG flow. And we will try to make sense of this operation in a very concrete setup, which is perturbing any conformal super-Yang-Mills in 4 dimensions by the leading irrelevant deformation that preserves the full supersymmetry. Of course, the deformation will break conformal invariance and hence superconformal invariance, but all 16 supercharges in flat space are preserved. As I will review momentarily, the leading irrelevant operator turns out to have dimension 8, and it belongs to a short multiplet. And so in the infrared, generically, any flow that preserves the maximal supersymmetry is bound to take this form. So sorry, I don't know whether my slide is fully visible. Let me do this again. Well, maybe, okay, sorry, it's just, yes, it is. And so the motivation that brought us back to this whole problem has to do with this remarkable progress that has been achieved in 2 dimensions, making sense of something similar in spirit. You may have heard of this TT-bar deformation of homological and collaborators, where indeed something like that appears to be possible, and one is able to make a purely theoretic definition what it means to go against the RG flow for this very special deformation that turns out to, in some sense, be semi-topological and in integrable cases preserve integrability. So let me tell you a little bit more. So I mentioned some representation theory. Indeed, the leading irrelevant deformation, if you think about it for a moment, better be the top component of a short multiplet. Well, the top component because you need to preserve supersymmetry, and of a short multiplet because you want the dimension to be as small as possible. And a little bit of analysis will show that, okay, the top component of the leading 1/2 BPS superprimary is the deformation that corresponds to the exact marginal coupling, complexified coupling tau of the theory. And then the leading irrelevant deformation, which needs to be a scalar, turns out to be in the, not quite in the next, but in the next to next multiplet, this famous 1 of 5 representation operator, which is in the single trace version, the trace of the power of 4 scalar with ISO6 indices symmetric and traceless. And if you take the top component, you find something which has this characteristic structure of f to the 4 minus f square, which comes from the expansion of the de Born-Infid action. And this had to happen because the de Born-Infid action is maximally supersymmetric. And since, as I'm just telling you, this is the unique leading irrelevant deformation, then of course this had to take this structure. The representation theory is blind to the color structure of the theory, so there is a single trace version, which I've indicated here, as well as a double trace version, which I've indicated below. And you see the double trace version takes the form of stress energy tensor square plus marginal operator square plus dots to make it supersymmetric. And so this really very much looks like as close to a 4-dimensional supersymmetric version of TT-bar as you may hope. But there is no indication really that it has the same remarkable properties. And the way we will proceed is attempt to make sense of adding this deformation in conformal perturbation theory, defining what it means to go against the RG flow order by order in the deformation parameter. So why would you be interested in such a thing? Well, there are many, sorry, what happened? Can you still see my full screen?
Yes, but we see many slides now, not just
yeah,
one.
Sorry, something happened. Is this better now?
It's,
Is it back to normal?
we see half and half now. So we see a bit of the first slide and a bit of the second.
How about now?
So now we see the full slide.
Okay, sorry about that. So why you may be interested in such a thing? Well, there are many interesting maximum supersymmetric flows that you can contemplate. For example, if you flow between n equal 4 superpyramid with the number of color n, and you move on the Coulomb branch, then in the infrared, you may get a smaller number of colors. Or perhaps you can start from the 6-dimensional 2,0 theory on a torus, and in the infrared, you will get n equal 4 superpyramids. But the real motivation for this work, although as you will see, we haven't quite solved this difficult problem that we wanted to solve, has to do indeed with open field theory, with the open field theory on ND3 branes in type 2B. And there, of course, it's a maximally supersymmetric theory that in the far infrared would become n equal 4 superpyramids, and then this deformation parameter A should be just alpha prime squared. And there's a long-standing speculation, which in some ways even predates ADS-FT itself. It was implicit in the earlier work of Klebanov and collaborator, of trying to generalize the standard ADS-FT duality between the near horizon geometry of the D3-brane metric, which is of course ADS5 times S5 and n equal 4 superior mills, to the full D3-brane geometry, where you keep the flat space asymptotic throat. So this is the metric here of the full D3-brane geometry, and we have kept here the constant H tilde. And long ago, in the early days of ADS-FT, integrators speculated that the role of this H tilde is precisely to deform n equal 4 superior mids by this irrelevant operator. And of course, the main question you have to answer here to make sense of this proposal, what does this all mean? Is this just a shorthand for the full open stream field theory? What am I supposed to do the moment that I bring down insertions of the relevant operator and counter divergence? There would be counter terms. Clearly, there are dots here. How do I specify the dots? And genetically, purely in field theoretic terms, you're not going to be able to make sense of this unless you have an additional principle. And well, nevertheless, Zamolodchikov taught us what to do in 2 dimensions. So is there a sense in which we can make progress along these lines? And so to leading order in H tilde, you don't have to answer any of these difficult questions. And long ago, with Marwan Ramsdorf, we showed that indeed this proposal works a leading order in H tilde, and we would like to make progress beyond to higher orders. As you shall see, we haven't quite solved the problem, but in the process, we have learned a few things. So to make progress, so the novelty of our approach is that we will not study the theory in flat space, but on the cylinder, on S3 times R. The moment you do that, you're really changing the problem. And so it's unclear whether you're really going to make contact with the full D3-brane geometry. I will make some comments about this at the end. Nevertheless, the problem is perfectly well defined in its own right. So as the deformation parameter is 0, of course, studying the theory on the cylinder in R4 makes no difference. They're related by a Weyl transformation, and the full PSU 2/4 superalgebra is preserved. The moment you turn on the deformation, then all you can hope to do is preserve the subgroup of non-conformal superisometries. And it turns out it's a very nice subalgebra. It's PSU 2/2 square times R2. And this is the supersymmetrization of the bosonic isometries, which is SO4, the isometry of the 3-sphere, R tau, where tau is the time direction on the cylinder. Obviously, these are isometries, and we can decompose them in SU2 times SU2. These subscript here refer to the indices that we use to parameterize the groups. You're probably going to forget them, but later on, these indices, alpha and alpha theta, will play a role. And the full SO6 art symmetry is actually broken down to SO4 times U1, which we can also write as SU2 times SU2 times U1. And what happens in the super symmetrization is that the SU2 of the spatial isometries and the SU2 of the art symmetry pair up into one copy of PSU22 for the first and another copy for the second, and they have a common central extension, which is the difference of the time translation generator H minus J being the generator of this additional SO2 or U1 art symmetry. And so the first technical complication is that the moment you add this deformation, you must supplement it with curvature corrections in order to preserve supersymmetry. And this is in general a very hard problem, particularly because the fact that the deformation is irrelevant makes this expansion infinite in the radius of S3L. But thankfully, we were able to find a very elegant, surprisingly elegant. So this is perhaps telling us something deeper, the fact that we really were able to find a beautiful off-shell formulation, which really followed closely previous work by Nathan Berkowitz, Evans, and Princeton, where we're able to realize 8 of the 16 supersymmetries. For example, we could pick the one with J equal 1/2. And the way this works, following the lead of this gentleman, we need to introduce 7 auxiliary fields, which we can split as 3 + 4. So 3 are transformed as special vectors of S3, and the other 4 are vectors of the SO4 art symmetry. And this allows us to preserve the full bosonic isometries of the background and 16 supersymmetry. 8 are realized off-shell, and the other 8 are, one can check, they are realized off-shell, provided you turn on a certain U1 background connection along the time direction. And so I'm not going to write the formulas because they're very complicated, but the way this works, you set up a little superspace formalism where you split the 6-scalar field as z, z bar, and phi a tilde, a dot. This is familiar in people who work in integrability. Z is a thing that is charged under J, and the other are the other 4 scalar, which are by fundamental SU2 times SU2 art symmetry. And then in terms of a superfield which you can introduce, the deformation takes this, deceivingly simple form, because of course everything is hidden down the superfield, which are just deforming by, integral over half of superspace of trace z bar to the 4th. Really could not be as simpler. And then as you integrate out the auxiliary field, this generates an infinite expansion in H. So to leading order, the story looks like this. You have n equal 4 super Yang-Mills, and then you perturb, of course, by the original 08, but as you can see, there are additional 1/L corrections, which are really the lower members of the same supermultiplet. And so, for example, the lowest component of 4 is the SO4 times 1 single component of the 1/5 superprimary. And so it's clear that these terms break the full art symmetry, for example, from SO6 down to SO4 times SO2 or U1. This is the classical story, but of course, I started by emphasizing very strongly the fact that at the quantum level, there will be ambiguities. There will be, in particular, D terms that are not in any way fixed by representation here, infinite tower of D terms that, there's no problem, of course, in adding those counter terms to remove divergences, but what about the finite part? The finite part is intrinsically ambiguous, and you need some other principle. So the principle that we like to invoke, and so this will hopefully make sense in our ideology that I've tried to motivate so far, is integrability. So famously, n equal 4 super Yang-Mills is integrable. Integrability leads to the full solution of the problem. And so could it be that this irrelevant deformation preserves integrability? Or to be more precise, could it be that there is a choice of counter terms as we go up the RG flow that we can fine tune in such a way that there is a preferred RG trajectory that preserves planar integrability? And so this is really the motivation to study the theory on the cylinder, because on the cylinder we have a perfectly well-defined sense in which we can study the integrability question. Because although, of course, the state operator map is lost away from the conformal fixed point, we can still think about states. They are the states in the quantization given by the time translation of the cylinder. And we can study their energies and see how the energy spectrum evolves from the planar spectral problem has been solved for n equals to 4 as we turn on this parameter H. And we can do this using the usual spin chain language of planar n equals 4 super Yang-Mills, in which states are in one-to-one correspondence with states of a spin chain with a certain Hamiltonian, which in our case we know the function of G squared, the Toff coupling, and H. And so the whole language of spin chains and n equal 4 integrability goes through, and now we just need to study whether this deformation preserves integrability. So in particular, deformation is Hermitian. There's a certain parity transformation that flips the order of states on the spin chain, the same as in n equals to 4, and so we can borrow much of the same language. Now, what really motivated me to revisit this problem seriously, you can always hope in life, right? I have many hopes and aspirations, but I don't pursue them all. And the reason I decided to pursue this one is because something really remarkable happens, that by putting the theory on the cylinder, of course, we're breaking the full superalgebra, but what are we breaking it down to? As I emphasized, we're breaking it down to this SU2/2 squared. But those familiar with the n equal 4 integrability story will recognize that SU2/2 is precisely all that was needed, really, to solve the spectral problem. Beautiful work by many authors. This was the key algebra. And in particular, let me remind you this very nice story of Beiser. He realized that this algebra has a triple central extension, not just H minus J, which I emphasized earlier, but there are two additional central extensions which appear in Q squared and S squared. And those are identically zero on gauge invariant states, but are non-zero on an open chain. And so if you consider the Manon propagation on an open chain, you will see that it's charged under these centrally extended elements. And that reasoning is enough to fix the dispersion relation of a single Manon to all orders in the coupling. Now, in our story, it's a little bit unclear what the coupling is. It's some coupling alpha, which really is a non-trivial function of both the Toff coupling and H. But nevertheless, apart from that ambiguity, the story goes through completely. And so remarkably, the Manons remain gapless. As you send the momentum to zero, the energy goes to the DPS bound, despite the fact that in our case, they are not Goldstone bosons. In the N=4 superior Mills case, you could argue that there had to be gapless because they're the Goldstone bosons of the spontaneous breaking of the symmetry down to this SU2/2 square, which is given by choosing the BMN vacuum. But in our case, that symmetry is explicitly broken. Nevertheless, the dispersion relation is essentially the same. Moreover, the two-body S matrix is uniquely fixed by this centrally extended symmetry up to an overall phase. And the Yang-Baxter equation is automatically satisfied. So really, the only difference of the deformation is in the dressing phase. And so if the problem wants to be integrable, it has all the structural features that it needs to be integrable, because we really simply need to choose a dressing phase that would make end-to-end scattering factorize. Of course, this is now a dynamical question. The fact that you have integrability in 2 to 2, namely Yang-Baxter, is not enough to guarantee that end-to-end will factorize, but nevertheless, all the structural features are there. And so to answer whether or not there is dynamical factorization, we need to do some calculation, which we did. So again, we work in conformal perturbation theory as a function of this parameter H, and we restrict to a certain subsector, which is analogous, for those of you who are familiar with, to the SU2/3 subsector of N=4 superior Mills. So there are two scalars, two fermions, there are three scalars really, three scalars, phi A has two indices, and Z is singled out, and two fermions. In the N=4 superior Mills case, these three complex scalar were on the same footing, and so we had an SU3 symmetry. In our story, that SU3 has been broken to SU2 times U1, and so the total superalgebra is SU2/2 times U1. And we can fix the dilation operator, order by order in perturbation theory. The most efficient way to do it is purely imposing the symmetry algebra, again, following work by Weisert. And so we can organize the expansion in terms of nearest neighbor, next to nearest neighbor, etc. You may be tempted to call that the loop order, although the loop can be either mean you have 1 power of G square of H, they're really on the same footing in terms of this expansion. And so the story, of course, is a bit technical. I will not give you the details, only the result. So we can, following Weisert, we can parameterize the Hamiltonian in terms of structures. Thank you, I have 5 minutes and I will need them all. We'll parameterize the structure in terms of, for example, this is an N to M neighbor kind of interaction. And we parameterize the generator, the superalgebra in terms of this kind of interactions. And then by imposing closure of the algebra and all the other symmetry, hermiticity, and parity, when the dust settles, you find that up to similarity transformation, the one loop Hamiltonian turns out to be uniquely fixed up to an overall parameter, which you can identify as the coupling. But of course, if it is uniquely fixed, it means that the deformation really to this order does nothing except redefining the coupling, right? So because we found that the symmetry alone, although we impose a smaller symmetry in N=4 case, was enough to fix the result uniquely. And so we land back on the one loop Hamiltonian of N=4, which of course is integrable, but this is not much of a test. And so we were brave, and it helps to have great collaborators. And again, I'm suppressing very complicated formulas, but two loops calculation is quite horrendous, but can be done. And when the dust settles, you again find the same, unfortunately, the same result, that even up to two loops, the deformation makes no difference. there is a sort of accidental symmetry enhancement and back to the symmetry of n equals to 4. And so we still have the integrable Hamiltonian of n equals to 4, but just because symmetry fixed it to be the same. But of course, this is a low loop accident, right? I mean, we certainly don't expect that that a higher loop this will persist. Eventually, the symmetry will not be enough to fix the Hamiltonian uniquely, and you will find a genuine deviation from n equals to 4. But at the moment, that's a little bit out of reach. Maybe we can do 3 loops. It's unclear that whether we will have the strength to do it, but eventually you need something more structural. And so, okay, on the plus side is that we didn't rule integrability out, but to be honest, we didn't rule it in either because we couldn't really make a dynamical test beyond the structural properties I mentioned. However, we can ask the following structural question. So, does there even exist an integrable long-range spin chain which is different from the n equal to 4 case that has the requisite properties? And here the analysis really is a little bit technical if you're not familiar with this whole integrability literature, but the short answer is yes. We see no real obstacle in just manufacturing, forget about field theory. Let's not just manufacture a long-range spin chain which has the symmetries of the problem, is integrable, and is potentially rising from this deformation of n equal 4 superior mills by an irrelevant operator. And the way this works is essentially by generalizing previous work by this gentleman. They considered a much simpler case of XXZ chain, and they found that they could construct order by order a less and less local spin chain by adding terms to the action which are proportional to the integrable charges of the original chain. And these are these QR, QS written as function of rapidity. So this is the solution of the chain in terms of some beta ansatz, and this beta and eta are parameters. So there really is a huge moduli space of integrable chain that whose Hamiltonian depend on this beta and eta. And this is the solution by beta ansatz. So in our case, we need something a little bit more special because H bar will correspond to the gap in the XZ chain. So we need to send that to 0. But nevertheless, if you analyze this problem, you find that there still appears to be a large moduli space of possibility which can still be integrable. You have to impose crossing. We see no real obstacle in doing that. And so, of course, we don't know because perhaps the field theory will give you something very specific, which is not integrable, but we see no a priori obstacle in finding a long-range spin chain. And so now I go back to the original question of what does this all mean? Again, the problem we really wanted to solve was the deformation of the flat space theory, but we didn't quite know how to think of integrability there, so we put the theory on a 3 times R. But the moment you do that, as I was emphasizing already, you lose a little bit the hope of making contact with the asymptotically flat D3 brane background. What this deformation seems to be doing instead is being dual to the bubbling geometries of Lin, Lunin, and Maldacena in the following sense. So what are those bubbling geometry? You take n equal 4 superior mills on S3 times R, dual it's ADS5 times S5, and then you add additional D3 branes, which, for example, you can wrap around a 3-sphere of the ADS5, for example. Those are the so-called giant gravitons. Now, if you study the theory on those additional D3 branes, that will look like an irrelevant deformation of n equal 4 superior mills. A low energy has to be n equals to 4, and then by supersymmetry, the leading relevant deformation will be exactly the one that we considered. And so the theory on those additional D3 branes will very much look like our flow. And the speculation is that then the dual interpretation is in terms of the back-reacted geometry that you obtain by adding those additional giant gravitons, which is one of these LLM geometries. So those are defined. It's a very beautiful solution of type 2D supergravity, which can be fully specified by drawing a bicoloring of a plane, black and white. They correspond to certain boundary condition that you have to impose in supergravity. And morally speaking, this is some sort of global ADS version of a Coulomb branch flow, where we are considering states whose energy is of order n squared, and hence they're back-reactive. And so here is an example of bicoloring. A single black disk corresponds to ADS5 times S5, where the radius of the disk is related to just the radius of curvature. And the next simplest deformation would take this form. Okay, so I'm imposing here rotational symmetry in the plane. I didn't have to, but if I do so, then I'm preserving the full U1 art symmetry, which is what we have implicitly assumed so far. So we should impose this additional U1 if there's a more general story in which we break the U1, but for simplicity we can keep it, and then we have this this rotational symmetry, and then you'll be very tempted to say that our deformation H over in units, in dimensionless units, just correspond to the ratio of this radii. If you send R1 to infinity, you collapse back to the S5 times S5, and on the other hand, this corresponds to the relevant deformation that we consider. So that's a nice story. What about integrability? Well, unfortunately, the classical sigma model for this simplest kind of LLM deformation appears to be non-integrable by studying the geodesic motion. And so this leaves our story a little unclear. We're not giving up. It's still very possible that there will be a subset of the spin chain which is integrable. The classical sigma model non-integrability comes from master geodesics, and so it wouldn't really affect this story that we have considered here so far, which is for asymptotically large chains. It's also possible, at least in my naive mind, that the classical sigma model and the full string theory really would be quite different. After all, string theory requires us to gauge the sigma model, and so perhaps you could hope that integrability is restored. So I don't really know. The story is a bit unclear. And it's also possible that there is a different holographic interpretation of the story, which is, after all, integrable. So remember, we're doing something extremely generic. We're deforming the theory by an irrelevant operator, and so far we have only used very little, just the symmetries broken by the deformation. And so there's, of course, an infinite ambiguity in what you can do as you go upstream the RG flow, and so the story may really be richer than this. So I am basically done. So there are many things that one can keep doing. Again, we really first like to demonstrate that we can have this integrable logic spin chain with all the symmetries required by the problem, and show that it comes from field theory with a certain arch flow that will have to have a specific shape and have a certain interpretation. And then, of course, you can explore different geometries. In R4, this is the one we really wanted to do to make contact with the full open string field theory of D3 branes. And then there's also a very nice story with the double trace deformation that I haven't told you anything about. Thank you very much.
So thank you, Leonardo, for this very inspiring talk. And so we don't have so much time for questions, perhaps just one question, and then we will have a coffee break. So I think in principle, if people want to stay to discuss a little bit during the coffee break, there should be nothing wrong about that. But so if there is some question, please just go ahead. So I see Fan Wang. So please open up your microphone and ask.
Hi, so I have a question. So Leonardo, it seems that you focus on this irrelevant deformation with positive sign, right?
Well, the field theory analysis that we did on the, this purely algebraic analysis didn't really care about the sign. It's a perturbative.
Yeah, so that is related to my question. So in the usual TT bar deformation, the physics is very different depending on the sign.
Yeah, I mean, okay, so go ahead. I mean, is that the question?
Yeah, so here it depends on how D1 depend on H, right?
Yes.
So you find that.
I mean, the TT bar deformation was an inspiration, right? It's not that anything I did really had anything to do with TT bar. It was a vague inspiration that we used as a stimulus.
Right.
I mean, yes, it's entirely possible that the physics would be very different for the sign. There's one sign that clearly makes more sense than the other because it gives a bounded Hamiltonian.
Right.
Well, that's the one you should choose.
But do you know the explicit dependence of this D1? Also, I guess D2 for H4 that depends on H. The explicit dependence on H. The
explicit one, we don't. You're right. So that is something that So the analysis that we have done so far, in some sense, pairs the two couplings, G square and H, into a single coupling, and then you need to disentangle. So I think it's easy to see what it is. It's basically the sum as H. Okay, if you want to nail the sign, we could do it. It will take a few minutes, but we can nail the sign.
I see.
At two loops, you have to do a little bit more work on the field theory side to find precisely how the coupling gets normalized as a function of G square and H.
But then on this, in this LLM interpretation, that interpretation only makes sense for, H positive, right?
Yeah, if any part of the story makes sense, I'm certainly aware, I'm certainly willing to give up on one choice of sign.
Okay.
Okay, so thanks. So since this is a coffee break, I think in principle anything is free to discuss, but we have to close officially the session because then we have to leave time for other talks. So the idea is that we will meet again in 10 minutes from now, but so people who wants to continue discuss, just feel free to do it, of course. So I will
just
show up
sharing
again.
my screen, right? Presumably, and
yes, you can continue sharing your screen. I think
okay.
There is no problem. Yes.
Can I ask another question?
Hi.
Of course.
How are you?
Good,
okay.
Oh yeah. Sorry,
Are you funny? We're asking
I'm watching too many talks this week.
Yeah, I think someone is also talking.
But sorry.
I think Lionel Mason is unmuted.
Okay, so maybe I can ask my question. So, Bernard, do you know like at which loop order does the divergences need D term to need you to add D terms as counter terms once you turn on this 08?
I'm not exactly sure. I think already at two loops.
Already at two loops.
I think so, but I haven't done the precise analysis.
Okay,
so
because
another thing that, okay, I mean, of course, we could do the three loop calculations. I mean, I couldn't, but my collaborators could. But we're not very motivated because there's a very strong hunch that even at three loops, it will be the same again. So it will collapse back to n equals to 4. And the reason for it, I mean, it's not a very compelling reason, but if you recall, in n equals to 4, the dynamical phase only kicks in at 4 loops. Now, of course, the story here is a little different. You have less symmetry. But, by Murphy's law, there's certainly a very good chance that you have to go up to 4 loops.
I see.
To really see this difference. And that is really, I would say, even, that's really out of reach.
Right.
So I'm a little reluctant to invest a lot of energy into a three loop calculation, since there's a little bit of a hunch that, that again, you will have the symmetry enhancement.
Mm-hmm.
So I think you have to study the problem a little bit sideways, finding other ways to test integrability. And again, look, I mean, I really don't know whether this story will turn out to be integrable or not.
Right, you mentioned the LLM sigma model is not integrable, right?
The sigma model for this LLM geometry is not integrable. Now, of course, is that a no-go? I mean, this is something I don't really know. I mean, string theory utilizes a tiny subsector of the sigma model structure, right? Because you have to only look at physical states. And so string theory is not the same thing as the classical sigma model. I don't know of an example of a string theory that is integrable despite the sigma model being non-integrable. So perhaps one can make a sharp no-go theorem along those lines. But a priori, certainly, if the classical sigma model had turned out to be integral, of course, then we would have made a much stronger claim. So that is a little upsetting. But nevertheless, again, so as you can see, the story has several moving parts, and they're a little independent. So, the analysis we did on that purely used the symmetry and this conformal perturbation theory is completely agnostic about what kind of dual background you want to choose. And so, it's entirely possible that there's a different dual background which is integrable, and in the far infrared, it's by symmetry it has to take this form. So that that is indeed what appears to be suggested by this analysis of the long-range spin chain. I mean, in fact, if anything, there seems to be an embarrassment of riches. You can write down lots of long-range chains that appear to be integrable.
Mm-hmm.
Hi, Leonardo.
Yes. Hi.
It's William Lynch. I was just, so I have a few questions. One of them is if you abelianize this gauge group, do you get Born-Infeld?
Yes, I think so. If you abelianize it, you will get Born-Infeld. Now, the real question is, well, I haven't checked, to be honest, I haven't checked that, but it looks very much like something like Born-Infeld, yes. There was a group of people that early on, maybe 20 or 25 years ago, were obsessed by the question of, okay, the abelian Born-Infeld, of course, we all understand. And so whether or not, okay, so let me, if I go back to this slide, I mean, whether or not I take this thing and I write it out, it will precisely land me on Born-Infeld in the abelian case, I don't know. It would be a nice thing to check. But then the next question you could ask is, will you land on non-abelian? If that works, then you'll be tempted to say, okay, well, maybe I will land on non-abelian Born-Infeld if I consider non-abelian case. But I think that would be completely unmotivated.
Well, I
can always hope.
I sent you a direct message with a link to a paper by De Fosse and Severin and I forget who else. Sorry, but it's in the direct message to you. If you perhaps you already know it. It's about the uniqueness of abelian Born-Infeld. Now, of course, they're putting abelian in the title, but they're claiming something about how it's the unique thing that preserves the BPS structure of the theory. And,
yes.
and
okay,
no
so
other deformations that do
if that is
something
the case, then I think indeed then you will land on abelian Born-Infeld.
Okay. So, but they seem to have some
okay, that would be, thank you very much for the suggestion. That's something that it need to be nice to check. However, even if that works out, I see no compelling reason that the non-abelian case should work out because of this determ ambiguity, right? I mean,
right, exactly.
Yeah,
but I thought you were trying to fix that somehow with integrability.
We're certainly trying to fix that somehow with integrability, but that is precisely how is indeed the question.
Well, it sounds like when you're using integrability, you're trying to preserve the BPS structure of the theory or something like that, right? The structure of all the BPS
I don't know if they're
states.
related. I mean, they're related in some ways, but yeah, so there is an intrinsic ambiguity in these D terms, and so it's the non-abelian Born-Infeld is really defined from open string theory. You're supposed to do open string amplitude and see what happens. It's not clear to me that this formalism is doing that for you. I mean, it would be fantastic if it did, but given that there's this large ambiguity, I see no, I mean, but you know, one should think about it. Maybe, you know, as I was trying to say, there's something remarkably nice about this off-shell formalism. Perhaps this niceness is trying to tell you something. But.
Yeah, I was going to ask you, where's the off-shell being used so heavily?
Oh, okay. So again, there are several moving parts at the top. The first part, so when we did this conformal perturbation theory calculation, we used it. We did not use it at all. That was purely a symmetry-based analysis.
Right. But you sounded like you were trying to say that it's very important.
Well, I mean, ultimately, of course, you need it because you know symmetry will only take you so far. Eventually, you really need to look at exactly what the field theory looks like. And so that's how the field theory looks like at the classical level. And
Can you connect for me what that means in terms of, it sounds like you're saying off-shell supersymmetry is important for telling you what the theory exactly looks like.
In this case because you have to prove the theory in this curve space. And so the curve, so because of the fact that H is, whatever it is, it has units of length to the fourth.
Yeah.
already just at the classical level, forget about quantum correction, just to preserve supersymmetry at the classical level, you will need an infinite expansion in powers of H.
Mm-hmm. Okay, and that'll be fixed by off-shell supersymmetry.
Because something that goes like 1 over,
right.
You can have 1 over correction, and that means corrections as powers of H. And that's, of course, you can do that without an off-shell formalism by correcting the supersymmetry order by order in H, but of course it's a gigantic nightmare.
It doesn't, so again in the abelian, that gives Born-Infeld, right?
There are auxiliary fields here that, everything looks linear in H of shell, but of course, the moment you integrate the auxiliary fields, we generate this infinite expansion.
Right.
So that's,
the off-shell
what's nice about this formalism.
Yeah.
We didn't really use it to this conformability calculation, but if there is indeed, this is the kind of formalism that might help you getting a better handle of Born-Infeld.
Well, so you're of course aware that if you do that for the abelian case, you get Born-Infeld, right?
Yes.
Okay, so that's Bagger and Galperin.
Maybe it is obvious that this will indeed give you abelian.
Okay.
But the non-abelian one will be a little unless.
So I think it's time to restart with our session, and there will be time for discussion, and then you can also try to have like private discussions. There will be plenty. There is also this Slack web page that can be used for comments. So now it's time to introduce the next speaker. Is Shota Komatsu from IAS Princeton. Okay, so I can already see your screen, thanks a lot. And he's talking about the boundary state from Wilson loops. So please go ahead.
All right, so thank you very much. And let me first thank the organizers for putting together this wonderful workshop. And today I'm going to talk about 2 papers that are upcoming, which are done together with Yunfen Zhang, Ahmed Sever, who are both in CERN, and Eduardo Vescovi, who is in Imperial College London. So let me first give you the spoiler of my talk. So the main message of my talk is that in certain situations, you can understand a boundary state as a matrix product state. So before explaining what I really mean by this, so let me begin with the introduction. So as we all know that the boundary states are keys to understand the open-closed duality, both in perturbative string theory and string field theory. However, they are often defined in an indirect way, and some works are often needed to write down their explicit expressions. For instance, in perturbative string theory, they are often defined by the boundary conditions, which is like of this form. And you need to do a little bit of math in order to write down explicit expression in terms of the oscillators. And the situation is much more complicated in open string field theory because they are defined only by the solution to the equation of motion, which takes up this form. And it is a priori not obvious how to write down the boundary state for any given solution psi star. However, of course, like we know that there have been much progress in the open string field theory, and there are by now 2 proposals on how to write down B of psi in open string field theory. So the first proposal was made in this paper, in which they proposed a Wilson loop-like expression for the boundary state. Explaining the details of this construction is certainly above my pay grade, but let me just give you a flavor of what it means. So if you take a full open string Hilbert space and take a trace over it, then you get this annulus diagram. And what they are proposing is instead of taking a trace over full Hilbert space, you take a trace over what's called half string Hilbert space, and you also insert arbitrary number of the solutions. Then as a result, you get this kind of like a diagram. And the claim is that you can basically read off the boundary state corresponding to the solution psi star by looking at the state living on this dashed line. Okay. And the other proposal was made in this paper, in which they basically explained how to compute the overlap between the boundary state and the closed string state, including the offshore ones, using some observable, which you can compute from the string field theory, which is nowadays called Elwood invariance. And by computing this overlap for like all possible closed string states, you can basically reconstruct the boundary state. So today, I'm going to address a similar question in n equals 4 super Mills in 4 dimensions, which is due to closed string theory in ADS 5 times S5 spacetime. But I should emphasize that my analysis would be entirely within n equals 4 super Mills. So more precisely, the question that I'm going to address is as follows. Can we express the Wilson loop in n equals 4 mills at weak coupling as a boundary state, as some sort of boundary state in the closed string Hilbert space? So here I put a quotation mark to the closed string because, as I said, my analysis will be entirely within n equals 4 mills. So I first need to clarify what I mean by the closed string, which I will do in the next slide. And the strategy of the computation is to first compute the analog of this overlap, like in this paper. And then I will arrive at an expression similar to the one given in this paper. And furthermore, I'm going to demonstrate that for the half PPS circular Wilson loop, one can actually uplift the solution that I construct at weak coupling to finite to foot coupling using integrability of n equals 4 mills. So that's the plan of the talk. So let me begin with the weak coupling story. So let me first clarify the setup. So in n equals 4 mills series, especially in the planar limit, the most fundamental observables are single trace local operators, which are of this form, where x and z are some like a scalars contained in n equals 4 mills. And it is known that the single trace local operators are dual to onshore closed string states in ADS5 times S5 spacetime. And pictorially, it's like this. So you insert the operator or at the boundary of ADS, then that's going to emit some state, which is onshore closed string state, which I denoted by V. On the other hand, if you consider the Wilson loop in fundamental representation, it is known to be dual to a disk worldsheet with the boundary ending on the contour of the Wilson loop. And pictorially, it is like this. So you have a Wilson loop and you have a string worldsheet, which is topologically disk, attaching to the Wilson loop. So here, I'm considering a small generalization of the Wilson loop, which is often called locally supersymmetric Wilson loop, which couples to scalar as well as to the gauge field. And from this picture, it's kind of obvious that this Wilson loop should correspond to some boundary state on the string worldsheet. So now, from combining these two observations, this suggests that the analog of the overlap should be the correlation function of the single trace local operator and the Wilson loop. So, and this is precisely what I'm going to talk about in the rest of my talk. So in the rest of my talk, I'm going to compute this object at weak coupling in 4 steps. But before explaining the details of the steps, let me just emphasize the 2 key ideas. So the first key idea is to use the generating function of the Wilson loops rather than considering individual Wilson loops. And the second key step is to express the Wilson loop as one-dimensional fermion. So let me begin with the step 1. So the generating function of the Wilson loop that I'm going to consider is this one. So instead of considering the usual Wilson loop, which is a trace of the path ordered exponential, I'm considering the determinant of identity matrix plus e to IA, which is the chemical potential that I introduced, times path ordered exponential. And if you expand this object in powers of e to IA, then at the leading order, you just get 1. And at the next leading order, you get e to IA times the Wilson loop in the fundamental representation. At the next to next leading order, you get Wilson loop in the rank to antisymmetric representation. And if you just want to recover the fundamental representation, you can do so by just doing the Fourier transformation. And the nice thing about this Z of A is that Z of A can be expressed as a path integral of one-dimensional fermion living on the contour of the Wilson loop. And more precisely, you can actually express this Z of A in this way, where chi and chi dagger is their fermion, and the action of the fermion is given by this expression. And as I wrote here, this chi is in the fundamental representation of the gauge group, whereas this chi dagger is in the anti-fundamental representation of the gauge group. In order to see the relation between this expansion and this path integral, it is actually nice to go to the Hamiltonian formalism of this fermion system and express this partition function as a trace over the fermion Hilbert space. Then you can see that there is a factor e to IA times chi dagger chi, which is nothing but the number operator of the fermion. And if you compare this expression and this expression, you immediately see that the fundamental representation corresponds to one particle state in fermion, and the rank 2 antisymmetric representation corresponds to 2 particle states of the fermion. So this was the step 1. And in the step 2, I'm going to integrate out n equals 4 super-mils. So for simplicity, I'm going to consider like free n equals 4 super-mils. And also I'm focusing on like the expectation value of this Wilson loop rather than correlation function between the operator and the Wilson loop. And so the path integral that I need to do is this one. So it's the path this is the path integral of n equals 4 fields, and this is the path integral of like a one-day fermion. And the action is given by this coupled system. Here I rewrote the action slightly to make it clear that this fermion or the Wilson loop is a source term for n equals 4 super-mils field phi I. Okay. Now, so this is the action that I'm going to consider. Now, because I'm working at tree level or free n equals 4 with free n equals 4 super-mils, I can easily integrate out n equals 4 super-mils field by using the usual like a Gaussian integration formula, which basically says that the Gaussian integral with the source term is given by this like a bilinear terms of the source term, where K inverse is the inverse of the kinetic term, which is nothing but the propagator. And if I apply this logic, I get this effective action of fermion, effective path integral of fermion. And here I have a quartic interaction of the fermion just because the source term itself was quadratic. And this Y is basically the propagator, which connects like 2 points on the Wilson loop. So this is a contribution from the gauge field, and this is a contribution from the scalar field. Okay. And now I need to deal with this action, which contains quartic interaction of the fermion. But of course, like there is a very, very canonical way of dealing with the quartic interaction of the fermion, which is to use the Hubbard-Stratonovich transformation. So the idea is to integrate in a bilocal field, rho tau tau prime, which roughly corresponds to the bilinear fermion, like a chi-dagger tau and a chi-dagger tau prime. And if I integrate in, then I get this action. And from this action, you can always go back to the original action by integrating out rows. So there are 2 nice features about this action. So the first nice feature is that there is a piece of the action which is multiplied by NC, which basically suggests that we can, in the large N limit, we can evaluate this path integral using the subtle point approximation. Another nice feature is that now the fermion action is purely quadratic, so you can just easily integrate it out. So let's do it. So that's the step 4, the final step. And so the idea is to take this action and do the fermion path integral. Of course, you get determinant. But an important point is that, as I said earlier, this chi was in the fundamental representation, where this chi dagger was in the anti-fundamental representation, which means that it has NC component. And this is why I have a power of NC here. And if you combine this with the previous action, which was like a bilinear term of the row fields, then I get this nice effective action of the row, which is multiplied by NC overall. So now we know what to do. We just need to do the saddle point analysis. So what we need to do is to compute the saddle point, solve the saddle point equation, which is of this form, and find a saddle point and plug that into the answer. And that is going to give you the expectation value of Z of A, which is the generating function of the Wilson. However, what I really wanted to compute is not just the expectation value of Z of A, but the correlation function between the Z of A and the local operator. So let me explain how things change if I include the local operator, which is of this form, where I1 and I2 are basically flavor indices, and phi's are scalars. So in steps 1 and 2, I emphasize that chi's are the source term for the n equals 4 super-mils fields. Therefore, if you integrate out n equals 4 super-mils, this is basically the same as solving the equation motion with the source term. And if you do so, then you end up replacing this expression with this expression, where phi chi is basically a classical profile of the scalar field sourced by the fermion. So this is the explicit expression. And I should emphasize that each phi is a bilinear. So inside this trace, you have like many fermions. And in steps 3 and 4, I integrated out chi's by using the by after integrating in row fields. And this is, of course, the same as like doing the Wick contraction of chi's. And in principle, because we had many fermions inside this expression, the combinatorics of Wick contraction can be very complicated. However, there is something nice happens in the large N limit, because it turns the point is that if you look at the neighboring fermions, then the gauge indices of the fermions are contracted because you're basically taking the product of matrices. And it turns out like if you recontract these two fermions whose gauge indices are contracted, then you get the factor of delta AA, Kronecker delta AA, which is of course MC. On the other hand, if I do the different Wick contraction, like contracting this guy and this guy, then I don't get that factor. So this basically tells us that the leading large N Wick contribution is just coming from contracting these neighboring fermions. So this is what I need to do. And the fermion propagator is just given by this, which is the inverse of the kinetic term for the fermion. And if I do this, then I will arrive at this expression. I have like a multiple integral of taus, and then I have like m tau 0 tau 1, which is basically coming from this Wick contraction. So this m tau tau prime contains two pieces. The first piece is basically the propagator of the fermion, and the second piece is basically something that I hide it in this dot dot dot. And an interesting observation is that you can view this like a multiple integral of tau as some kind of like operator trace, where the indices of the matrices are now replaced by like a continuous label tau. So you like you multiply this operator much like the matrices, and then like sum over indices, which is now replaced with the integral of taus. So this is the operator trace. And there is also like a very simple way of like understanding it geometrically. So if you consider the planar Wick contraction between Wilson loop and a local operator, then you get this kind of diagram, and where these are propagators. And this part, which is the propagator of fermion, is roughly speaking corresponding to this part. It's the propagation of the fermion along the Wilson line. Whereas this part is coming from some like interaction between fermion and then this propagator. And if you continue many times, and then you take a trace, and that's why you get this kind of expression. Okay, so and another nice thing is that alternatively, you can also write this in this way. So the idea is to introduce some state corresponding to the operator, so where i's are basically indices, flavor indices of the scalar contained in operator O. And I also prepare some state, which is given by this operator trace and j times j, and I sum over j's. And if I do the contraction or compute the overlap between this guy and this guy, I basically end up projecting to a particular component of this sum, and then I recover the original expression, which is this one. But a nice thing about this is that this is precisely what people normally call the matrix product state. And if I use the conventional like pictorial representation of the matrix product state, I can express this one in this way. So here I do some tau integration over which I'm taking a trace. And then here there are some open indices where I read off the state. But I should say that this is a little bit unusual matrix product state, because normally when people talk about a matrix product state, the dimension of the Hilbert space that people use is typically like a discrete and finite. here, instead, I have like a continuous and infinite bond dimension. But I should also say that this continuous infinite can be replaced by the discrete infinite dimensional matrices by simply using the mode expansion. And another interesting feature is that in some sense, this matrix product state is a discretized analog of the expression that obtained in this paper. So in order to see this, it's best to just draw figures. So this is basically the matrix product state that I constructed, and I can read off the state from here. So I'm doing the tau trace, and I read off the state here. And this is the like about Wilson loop representation of the boundary state constructed in this paper. And here I do like a half string Hilbert space path integral, and I read off the state here. So in the hindsight, this construction was in some sense also the matrix product state. So let me just give you some nice application of this construction. And a simple application of this is to consider the half PPS circular Wilson loop. And in the case of half PPS circular Wilson loop, you can actually simplify the subtle weak point equation for rho by using the mode expansion, because there's some nice symmetry of rotating the circle. And using the mode expansion, the subtle point equation is given by this, and you can solve it explicitly in this way. The details is actually not very important, but what's important is that it actually contains a square root. So that is going to be important in the next slide. And furthermore, if O is also BPS operator, by which I mean O is like just a simple operator like this, after using the mode expansion, I can replace like a tau trace that I wrote in the previous slide, okay, with this expression. And furthermore, a nice thing about this is that actually it turns out that this matrix is actually like a proportional to the Kronecker delta. So this trace reduces to a single sum. And this single sum, you can actually easily do it by simply using the Sommerfeld-Watson transformation. So the idea is to replace the single, like a sum over integer by some contour integral by putting in some like a tangent function, and then deforming the contour and then making it encircle around the branch cut contained in rho, which is a square root branch cut. And after doing so, I get this expression. And if you further project it to the fundamental representation and using this usual like a Fourier transformation, then I get this expression. And this can be evaluated explicitly and gives you the famous Bessel function, which was obtained by the localization. So this was the story for BPS operator. But for non-BPS operator, of course, we need to do a bit of work, because so far we've been only working at tree level. For non-BPS operator, interaction terms do contribute to the final answer. And in order to do that, I will resort to the worldsheet description of this guy. And as I mentioned earlier, the ADS-CFT relates this correlation function with some disk with one puncture, which is of this form, which alternatively can be expressed as the overlap between the closed string state and the boundary state. And in some sense, the matrix product state that I constructed earlier is the weak coupling limit of this boundary state. And the goal of the rest of my talk, like maybe in 3 or 4 minutes, is to determine this boundary state at finite coupling using integrability. And in order to do so, I'm going to resort to the bootstrap program. Although I don't have time to tell it, but if you do the computation explicitly for weak coupling for non-BPS operator, you see some patterns, which is some like unexpected selection rule. This basically suggests that there is a hidden symmetry, and furthermore, in particular, suggests that B is what's called integrable boundary state. So there are two nice properties of the integrable boundary state. And the first one is that for the integrable boundary state, if you consider overlap between the boundary state and some multi-particle states on the worldsheet, then it actually kind of factorizes into two-particle overlap. And the second nice thing is that you can actually constrain this object by solving the set of axioms. And by solving it, you can actually compute it at finite coupling. And here are the set of axioms, but let me just skip it. So the most important one is the boundary version of Yang-Baxter equation, which I denoted here using picture. And if you solve these actions, you find that there is a family of one parameter family of solution and parameterized by this A. And if you look at the solution, then you see that there is a pole at A plus minus I over 2. And much like the poles in the S matrix, poles in this overlap actually signal some kind of boundary, like some kind of bound state, which can be thought of as some excited boundary state. And the overlap for the excited boundary state can again be determined by using the bootstrap axiom. And if you compute this object using the overlap axiom, then you find a new pole, and it actually continues. And repeating this procedure, you find infinitely many boundary states, and the final answer is given by, again, infinite sum of integers. And this, you can again do the Sommerfeld-Watson transformation, and you finally arrive at this kind of expression. So, and let me just make some remarks about this expression. So for non-BPS operator, you can also do the computation of weak coupling explicitly using perturbation theory. And this expression reduces to the weak coupling result computed by spin chain methods. And for BPS operator, you basically just need to set all these factors to 1, then you recover the localization result. An interesting feature of this is that in this bootstrap analysis, I obtain this expression by summing over all possible excited boundary states. Whereas in the weak coupling analysis, I obtain this kind of expression by summing over the bond dimension of the matrix product state. So it seems there is some nice relation between the number of excited states, number of excited boundary state, and the bond dimension in matrix product state. And this is particularly interesting because usually the auxiliary Hilbert space of matrix product state doesn't have any physical meaning, but this is basically telling us that in this particular case, it is actually the degrees of freedom living on the boundary. So let me end with the conclusion. So these are summaries of what I did. And these are basically the future direction. But let me just say, like, as for the future direction, maybe it's also interesting to consider other setup, which is also given by some like a boundary or overlap between boundary state and a closed string state. One possible arena is to understand the instantons in n equals 4 dependence. And also it would be nice if you can connect the weak coupling and the strong finite coupling description, maybe in a simpler model like C1 string. So let me end here.
So thanks a lot, Shota, for this very inspiring talk. So we have some 4 minutes for questions. So just open up your microphone and ask if you have questions, please.
I had a question. So it's very nice talk. You mentioned the word worldsheet, but you don't say what worldsheet you're using. What is the string theory you're using?
Right. So it's basically like I would say gauge fixed Green-Schwarz action whose target space data is 5 times 5.
And how do you integrate over the worldsheet fermions? Do you, or what are your worldsheet fields?
Well, it's the usual Green-Schwarz worldsheets, the Green-Schwarz theory, target space data is 5 times 5 in the light congauge. But I'm not going to explicitly like dealing with the worldsheet fields. Instead, like I'm just using the bootstrap method. Like just imposing some consistency condition and computing the overlap. Does that answer your question? Mm-hmm.
I guess so. So it's Green-Schwarz light cone gauge in ADS 5 times S5, is that
right? Right.
So you don't preserve all the PSU to 2,4, you just preserve some stuff?
Yeah, just PSU 2/2 square, the same symmetry as Leonardo talked about.
And you have BC goes, so you don't, it's just light cone.
No, it's light cone, yeah. So you only see like physical degrees of freedom.
Okay, thanks.
Sorry.
Shota, can I ask a simple nice question? So at large n, you said that the fermions, they need to couple to neighbors. There was some rule like that?
Right.
What is the holographic picture for that?
Well, it's basically, okay, so on the gauge theory side, it's basically coming from planarity. So it's just like a weird manifestation of the planarity. So I would say it should be coming from the fact that you are just considering this worldsheet, but I cannot like give a clear answer right now.
So I had another question. Do you have to do large R charge then if you're doing Green-Schwarz light cone?
Okay, so when you formulate the bootstrap axiom, then you need to go to the large R charge because you want to have some kind of notion of asymptotic state. Okay. But then after that you can compactify.
Are there other questions? So maybe I have a naive question. How are you going to link this boundary state construction with your idea of studying instanton from ADHM in n=4 superior mills?
Okay, so the reason why I said ADHM is that this fermion, like the idea of introducing this like a fermion which is in the fundamental representation, is actually kind of inspired by the ADHM construction in which you express like a instanton solution by introducing auxiliary matrices, and some of which are actually fundamental. So that's why I was saying that I wrote ADHM here. So maybe like if you properly replace the fermion that I talked about with some fields in ADHM construction, maybe like something similar can just work out.
So I guess they should be related to the possibility of creating D-1 brane in the bulk and reading them off from the Wilson loop somehow.
Right. So in our case of Wilson loop, those fermions are precisely some like open string stretching between the probe D brane described in Wilson loop and n=4 septembers, and you just need to replace it with D-instanton.
I see. Okay, thanks. Okay. So if there are no other questions, we can thank Shota again, and we can pass to the next speaker. Is Xi Jin? Xi is around?
Yes.
Okay, hi Xi. So you can try to share your screen.
Oh yeah, actually, can you make my other, like my iPad as the co-host so I can, because I think...
Oh, I think this is Nathan that should do it.
Yeah, just tell me what your iPad is called.
Do it.
It's also under my name. It's the other, it's under my other name.
Okay, I found it. Okay.
Okay.
Great.
So next speaker. Okay, well, let's see if I cannot see your screen yet.
It's on there.
Okay, so now I think it's working.
Okay.
Okay, very good. So next speaker is Xi Yin from Harvard, and he's going to tell us about the instanton calculus in C=1 string theory. So please go ahead.
Thank you very much for the invitation. So I will talk about some couple of papers I wrote with Bruno Balthazar and Victor Rodriguez at the end of last year. Our understanding of worldsheet formulation of string theory is often said that it's a level of perturbation theory, but we can do a little bit beyond that in principle. So we know that the worldsheet formulation of string theory derives to a genus expansion, and this expansion typically is expected to be a asymptotic series, perhaps has zero radius convergence. And one can imagine that possibly can make sense of that by some resummation, but we'll understand that in many examples, crucially, that there are incident contributions, space-time incident contributions to string scattering amplitudes that goes beyond the genus expansion of the worldsheet perturbation theory. Now, these are the one basic class of instantons in string theory that we know are responsible for various effects are the so-called D-instantons. They are first, the existence was first emphasized by Joe Polchinski even before D-branes were recognized as objects in string theory, and they were concretely explored by Green and Gutzborough in the context of type 2B string theory in 1997. The basic idea is the following. So these D-instantons, these are these red dots. They're D-brane-like objects that are localized in space and time. These gray curves represent open strings. So from the space-time picture, these things are localized in space and time. In the worldsheet picture, they are boundary conditions. So they're possible boundary conditions for the scattering amplitudes of these closed string insertions. Now, unlike in quantum field theory, if you start with a path integral, at least formally, there's a derivation in some cases, in simple cases at least, of why you need instantons, which are saddle points of the Euclidean path integral, and you understand how to take account of their effects when you can specify the path integration contour in the field space. In string theory, we don't have such a first principle derivation of the D-instant prescription. And this difficulty is not just technical, but it's kind of conceptually, there's a conceptual obstacle, which is that, as we know, the D-instanton action, just like the D-brane, goes like 1 over the string coupling, 1 over D string, as opposed to 1 over D string square, whereas any kind of regular solution to some kind of closed string field action would evaluate to something of order 1 over D string squared. So the kind of qualitatively, you don't expect the D-instanton to be describable as a regular solution of a closed string field configuration. That's an admissible solution in closed string field theory. So there, I would say that up to now, there is no first principle prescription for how to compute systematically D-instant contribution to string amplitudes. But nonetheless, in many cases, we can kind of follow our nose and do it. And there are many consistent checks one can do. Part of the goal of this talk is trying to understand this dictionary in a specific setting. Now, I should say that, in fact, one of the basic puzzles you immediately encounter is, why are the D-instant effects even there to begin with? Or maybe to be more precise, how do you determine the normalization of the measure on the instanton moduli space? Again, in the field theory, you can derive this at the particle level by integrating over fluctuations around the saddle point, but we don't have such a prescription in string theory. In fact, in type 2B superstring theory, in some sense, you can interpret the work of Green and Gutzborough as fixing this normalization by invoking consistency with S duality. And the context equals 1 string theory, which I'll discuss in the rest of this talk, will fix the normalization by invoking the duality with the matrix quantum mechanics. Now, another kind of important thing in business here is that we'll need the so-called, what we call the Fischler-Susskind Polchinski mechanism for canceling divergence between worldsheet diagrams with boundaries that have different topologies due to the divergence of open string collecting modes being on shell. I'll come to this in more detail a bit later. So that was kind of non-trivial. In most of this talk, I'm going to take this low-tech approach of trying to compute on-shell worldsheet observables. Now, in each diagram, there will be divergence with the integral of the moduli space. We'll try to deal with the divergence when we see them, but this is not exactly rigorous nor the most systematic thing you can do. The more high-tech approach is what Ashoke has lectured on last week in his series, based on open plus closed string field theory. And I think he will have more to say today on that. Okay, now let me come to sequence-1 string theory. So the sequence-1 string theory is a nice model of string theory because it is the only known bosonic string theory that has a worldsheet description and amidst the space-time interpretation, I emphasize time here, and that is consistent just even at a level of perturbation theory at the quantum level. So in contrast to critical string theory, which does not make sense to the quantum level because it's tachyon. So this is, for that reason, it's a nice model, but the worldsheet theory is, slightly non-trivial for those who have not thought about this in detail. So you have the usual BC system coupled to a CFT of under charge 26, that consists of time-like boson, X naught as usual, and C=25 Liouville theory. The C=25 Liouville theory is special in that it has no relevant operator, no natural operator, and that's the reason that this theory is tachyon free. And the usual kind of Lagrangian description of the Liouville theory, one writes an action like this: there's a Liouville field phi, there's some background charge for phi, and so forth. I write this down just because I want to set up the convention. The vertex operators in Liouville theory, which are Virasoro primers, are these VP. They're labeled by this parameter P, which is the Liouville momentum. And this theory is fully interacting. In fact, the C=25 Liouville theory, you should view it as a strongly interacting conformal field theory. The only way I can define precisely in a priori what this Liouville vertex operator is I can say that it's wave functional in the asymptotic region where the Liouville field goes to minus infinity. This Liouville potential dies off. It looks like the form combination of incoming and outgoing plane wave in the space of the Liouville field phi. My normalization of the vertex operator is such that a two-point function is delta function normalized, as one would like in the CFE language. It is slightly different from older literature in which one of the plane wave components coefficient is normalized to 1, but that's not very natural for my purpose. This has to do, this slight difference has to do with the so-called Lechpole factor, which was notorious and caused some confusion historically. But for me, as once I start with work with these vertex operators, there's no Lechpole factor to worry about. For those of you who know what that is. The closing states are very simple in the Siegel-Schwann string theory. The only asymptotic states are labeled by the Liouville momentum and the vertex operator of this form. So this describes effectively a particle, a single scalar particle, let's say, moving 1 + 1d, the spatial direction being the Liouville direction, that is effectively massless in the asymptotic region. But when they come to a region of finite phi, there's non-trivial interaction. So importantly, this Siegel-Schwann string theory has a matrix quantum mechanics field due to the limitation of time. I won't get into this in detail. I'll just say that the dual matrix quantum mechanics has, at least within the closing sector, has can be described in terms of a system of free fermions that free a large number of free non-relative fermions moving in a potential like this upside down harmonic potential, and they fill the right side of the Fermi C in the perturbative level. Here's the picture of phase space. In the phase space, the fermions fill this droplet over here. Now the closed strings are not due to the fermions; they're due to particle-hole pairs of the Fermi C, or equivalently collective excitations of the Fermi surface. That's why the fermions are free, but the collective excitations are interacting. There's a well-defined prescription for computing the exact scattering amplitudes of these collecting modes. So I'm working h bar equals to 1 unit, and the height of this barrier here, which is mu, can be identified with inverse string coupling. The intuition is that in the regime of large mu, the Fermi C is semi-classical, and that corresponds to weak coupled string theory. So the interaction of these closing modes, which are due to the collective excitation of Fermi surface, are quantum effects from that perspective. Because the focus of this talk is going to be on the worldsheet aspect, I won't get into much of the details of the matrix model discussion. I'm just going to mention here that while the usual prescription of Siegel-Schwann matrix model, matrix quantum mechanics, is perturbative, so you fill one side of the Fermi C, but the fermions can tunnel to the other side, but the tunneling is suppressed. There's a natural non-perturbative completion of that state, where instead of saying I fill the right side of the Fermi C, here I fill all the energy eigenstates of the individual fermions, in which they occupy the scattering state where nothing comes in from the left. So things come from the right and they bounce back, and something comes to the left, but nothing comes in from the left. So these are states I fill, And this is the non-perturbative analog of the ground state that's supposed, quote unquote, ground state, not really the ground state, but the state that's supposed to be deal with the closed string vacuum. A curious fact is that if you, well, this fact will become important shortly. A curious fact is that if you take this prescription, you can calculate the scattering amplitude of these particle hole pairs, knowing the reflection amplitude of the particles and that of the hole, which depends on what this, this quote unquote ground state of the Fermi sea is. You take that result, you can consider, for example, something like a 1 to k scattering amplitude of these collective modes, and you expand in a weak coupling, which is a large mu. So if you do that expansion, you'll find that it takes the form of a very suggestive form. So there's a perturbative expansion in 1 over mu. Remember, 1 over mu is supposed to be identified with a string coupling of the factor of 2 pi. So this perturbative expansion looks exactly like a genus expansion. And if you look at this expansion closely in the specific theory, it's actually Borel summable. And if you define the sum to be the Borel sum answer, then on top of that, it turns out that there's an instanton expansion that looks like this. And these exponential factors are like the e to the minus n over gs. These are the instanton action suppression factors. And interestingly, at each instant order, or instant number n, the coefficients can further admit a perturbative expansion 1 over mu, but now they involve integer powers 1 over mu as opposed to even integer powers 1 over mu. So whereas in here you have a closed string perturbative expansion, here you have an open string perturbative expansion. So we'll now try to reproduce this expansion from the worldsheet perspective. So in the worldsheet description, we want to investigate D-instanton. More precisely, we want to investigate the contribution to closed string scattering amplitude that is mediated through the process mediated by the D-instanton. So we're going to consider a worldsheet with boundary, the boundary at the end on the D-instanton. So to begin with, we'll have to say, what are these D-instantons in sequence line string theory? What are the boundary conditions that are admissible? So let me begin with the simplest class of D-instantons. They're so-called ZZ instantons. So what they are is the most obvious thing you can try to do. So we said the worldsheet theory is this time-like boson tensor with Liouville theory. So we're going to take a boundary condition. That's the tensor product of the boundary condition. That is Dirichlet in time, therefore instanton, and a ZZ brane in Liouville theory. Now, some of you might know that the Liouville theory also admits another type of brane known as FZC branes, but those things are infinitely extending. They will have, and they will correspond instanton with infinite action. So we're going to restrict ourselves to instanton with finite action. So therefore, only the ZZ branes. So the ZZ branes, you can describe this in terms of the boundary state. This boundary state is known completely. So if you put this Liouville theory on a semi-infinite cylinder, put a boundary condition over here, the ZZ boundary condition. So the Zamolodchikov have bootstrapped all these ZZ boundary states. They're labeled by a pair of integers m and n, starting from 1, and they take the following form. So you can, of course, always expand the boundary state on the basis of the Ishibaki state, where BP was the, remember, that was the Liouville primary, labeled by Liouville momentum T, and the coefficient here is the disk 1-point function. I call it psi, and the Zamolodchikovs have solved the psi explicitly that they take this, given by this formula. Okay, so this is in the sequence 25 case. So this everything is completely explicit. We can speak of the instant action. The instant action, in some sense, you want to say it's an empty disk. Now, in Liouville theory, this is a bit tricky because we can say what the disk 1-point function is, but to go from this 1-point function to the empty disk, note that the identity operator is not a normalizable operator in Liouville theory. So it's a bit tricky. Now, we can think of the identity operator, you can arrive at identity operator in some sense by analytically continue this VP to imaginary value of P, which is not in the part of the spectrum. Okay. So anyway, by doing this little trick, you can figure out at least a relative normalization of the instanton action for the instantons of different types. So this analysis actually will show you that while we want to identify the most basic ZZ instant, which is labeled by this m and n equals to 1 and 1, which is the usual ZZ brane that people like to talk about for reasons I won't get into right now. So that its action will be identified with 1 over GS. And its interpretation of zero matrix model is just a bound. It's the bound solution. These other instantons, if they actually play a role, which is not obvious whether they play a role at the moment, by this trick you can show that you can argue that this action should be n times n times the most basic Z-instanton, which is 1 over GS. So this n comma n Z-instanton, you should think of this as some kind of higher instanton that have some extra instanton charge, even though there's no instanton charge, but have n times the instanton action of the most basic one. Okay, so now we're going to try to figure out the instanton expansion of closed string in the instant correction to closed string amplitude. So I'm just going to focus on the simplest, like 1-to-1 reflecting amplitude in the theory, which is already non-trivial. As I said, there's a 1-to-k generally. If you have one closed string coming in, so the real wall, many closed strings can be created and go back out to infinity. I'm just going to focus on 1-to-1 amplitude. So in this case, we have 2 closed string insertions on the worldsheet diagram. We can discuss the perturbative amplitude, but that's not part of the talk. So in this talk, I'm just going to focus on the instanton correction to the perturbative amplitude. And a leading order, we're talking about correction of the form e to the minus 1 over GS, and it has some dependence on the energy of the closed string, which are omega and omega prime, as you see in this diagram. Now, in this diagram, there are 2 disks. So this is the lowest order diagram that contributes to this amplitude. Now, it looks disconnected, but in fact, you should view this as a contribution to the connected amplitude because the 2 boundaries are ending on the same ZZ instanton. Okay, so it's 2 disconnected disks, but the 2 boundaries are on the same instanton. And the way you would calculate the diagram is the following. So you follow your node, and you first compute the usual worldsheet disk 1-point function with appropriate, fixing a component, killing brackets, and all that, with closed string operator insertion. And that's very easy to compute because we know that these 1-point functions in the Liouville theory with the boundary condition. You just need to add the ghost and the time boson, the time-like boson. And then it's weighted by this e to the minus instant. Actually, you can think of this as sometimes exponentiating the empty disk. And then you have an integration over the collected coordinate of instanton, which is what the parameter labels where it is in time. You can also think of this as an instant moduli space. As I said, well, in this case, it's obvious that there should be translation symmetry. So the measure is translation invariant in time, but you don't know what its normalization is a priori. So there's normalization factor n, curly n sitting in front. An answer after you integrate over the collected coordinates is that's going to impose energy conservation delta function. And this 1-point function to give this square dependence on the energy and this n. So you can compare this answer to the matrix quantum mechanics, and turns out that in a very rather than trivial way, even though this is quite a simple expression, it agrees with a 1-instant contribution at this order with the matrix quantum mechanics non-perturbative completion. And you can also fix the normalization factor. Okay, so this is at order e to the minus 1 over GS. You can go to next to leading order at 1-instant level, which is e to the minus 1 over GS times GS. This order, in fact, if you have attended Sen's lecture last week, has shown these diagrams. So you have the disk with 2 closed string insertions. But this diagram by itself, in fact, naively, this is the first one you might have thought about, but it's actually divergent. It's divergent because there's an open string propagation through this cut that's always on shelf. This open string lives in 0 plus 0 dimension. You don't get to change its momentum to take it off shelf. So it's always divergent. But divergence is cancelled by the diagram to other topology of this disk with annulus. So this is one diagram. This is a second diagram. This is a third diagram. And there's a fourth diagram which you can think of this with 2 hole as a order G string correction to the instant action itself. This diagram we did not actually calculate. This is very subtle. You have to regularize in various ways. But we'll assume that it's just some constant order GS. Now, it was in fact already pointed out by Polchinski back in '94 that this divergence, open string divergence between these 3 diagrams will cancel. But you might worry that because these divergences are of a logarithmic, of a logarithmic type, you might worry that, well, you can actually fix the finite part. So there's the a priori, if you only read Polchinski's paper in 94, you would worry that there's finite ambiguity. And in fact, when we wrote our paper first, our first paper on this, we encountered that ambiguity, which we decided that we're going to fix by conversing with the matrix model. But of course, now through the work of Ashoke, that can be fixed by string field theory, and I'll refer you to Ashoke's lecture for that. So if you just take these two parameters, two constant parameters, and fit against the matrix model answer. By the way, the matrix model answer for the contribution to the one-to-one amplitude at this order has it's some explicit function you can just write down. Okay, it's not completely trivial, but it's very explicit. It's this function here, this function of energy. So as you can see, it's relatively simple, but it's not so trivial to reproduce. And here's the numerical fit. So the blue curve is this function, and the red dots are the actual numerics we computed that fit in two parameters, and they agree pretty well. So I should say that most of the error or the difficulty in numerical computation has to do with computing this annulus one-point amplitude, one-point function in Liouville theory, because the only way I know how to compute this in Liouville theory is by integrating conformal blocks. So you can choose to decompose this in one or the other channel, depending on where you are in the moduli space, which is two-dimensional for the one-punctured annulus. And the relevant conformal block is actually a restriction of the holomorphic Virasoro conformal block with a torus 2 point. That's rather than trivial. You can continue using some recursion formula, but you have to truncate that series. Depending on where you are in the moduli space, there's some error. You have to kind of do some interpolation. So that's the source for this numerical error in this computation. And in the end, the parameters we fit, at least the finite ambiguity in this FSP mechanism cancellation, the answer we got agreed with what Ashoke found from string field theory within 1%, which we thought was reasonable given the errors we expected from this numerical integral, which is fairly complicated to do, in fact. So let me finally comment on the multi-instant contribution, which you can also do, which is rather nice. So the multi-instantons, so first of all, you have to say what the prescription is. So we're going to choose the Lorentzian contour for reasons that will become clear shortly. So you can have different instantons at different times. But intriguingly, we discovered that we have to include more than just the 1,1 DD branch, but also the n,1 type. Each D-instanton with n,1 type will come with a different normalization factor, which we also do not know a priori, but we can fix by comparison with the matrix quantum mechanics. So here's an example of what the two-instant contribution looks like at the leading order, which is e to the -2 over GS. This is, again, to the one-to-one scattering amplitude. I will just comment here that, so first of all, as I said, you have diagrams where you have one disk ending on one instanton and the other disk ending on the other instanton. You have diagrams where both disks end on the same instanton. You also have diagrams where the both disks end on the single instanton of the 2,1 type, which, as I mentioned earlier, has twice instant action of the basic one. And interesting here, one interesting aspect here is that for the two instantons of the basic type, there's this exponentiation of the cylinder diagram, which actually contributes to the measure factor. So this diagram can be calculated very easily. It's just an endless partition function with one boundary on one instanton, the other boundary on the other instanton, separated in time. And you can just calculate in the usual way. There's a Liouville part, there's a time-like boson part, the DZ goes contribution. These eta functions all cancel, and you end up with a simple expression like this. And if you exponentiate it, you get this factor. This is a correction to instant measure. This is the instant measure factor on the moduli space of two instantons, where delta XE is a Euclidean time separation between the two. So you see the numerator here is like a Vandermonde determinant factor, and the bottom denominator, which has a pole, when they're separated by 2 pi in Euclidean space, just has to do with the fact that there's open string tachyon between the two instantons that goes on shell. But if you choose the Lorentzian contour, this pole does not cause any problem in the integration. And after some combinatoric magic, which you can look at it in our paper, that we won't have time to discuss, everything matches with the matrix model at order e to the -n over GS for arbitrary integer n. So to conclude, So we think that the sequence-1 string theory defined by the worldsheet genus expansion together with the instanton D-instanton effect is actually non-perturbably complete to the extent that as far as the closed string, exclusively closed string amplitudes are concerned. This is largely partially possible only thanks to the Borel summability of perturbation series in this theory and absence of order e to minus 1 over ds square effect, which you expect to be typical of quantum gravity. This is perhaps a special feature of sequence-1 string theory that won't hold more generally. So far, we're restricted to the discussion of exclusive closed string amplitudes, which do not quite saturate unitarity. But nonetheless, you know, they're supposed to be exact within the closed string sector. But if you want to restore unitarity, you have to include additional states, which are perhaps these ZZ branes with open string tachyon rolled into the wrong side. So the folks, you know, in this conference who work on open string field theory have thought about this, I think, in the past, and I think, as far as I understand, there's no you know, conclusive results on this, but I think it's important to study this in context of sequence-1 string theory. It's possible to generalize this to the 0B case where you see both sides of the potential and save you from some of the complication of the tunneling. And we think there's some lesson we can learn about this for critical superstring theory. And currently we are in some work in progress. We're revisiting this analysis questions in type 2D string theory. So I'll stop here. Thank you.
So thanks a lot for this very nice talk. So we have some time for questions. So please just go ahead. Just open up your microphone and ask. So I have a quick question. So how would you see the effect of the FZZT brane in this framework?
You see, I'm restricting myself to the scattering amplitude of closed strings, and the FZZT branes do not play a role there because, well, as instantons, they will always have infinite action. They kind of, so maybe I should show a picture. The FZZT branes are like, so this is zero direction. FZZT branes are semi-infinite objects, extends all the way to the recovering region. Yeah. So these have infinite action. And in fact, they not only have infinite action, they change asymptotic. So they are not instantons in my story here. They don't contribute to the closed amplitude. Now, if you want to include FZZT branes, I would say that you are changing the background of sequence-1 string theory. So you're deforming the asymptotic. So in fact, I would view sequence-1 string theory with FZZT brane as a different background of sequence-1 string theory. And that's actually a very interesting thing. And in fact, we understand that it has something to do with going to the non-single sector of the matrix model. So, but you have to actually enlarge the matrix model if you want to incorporate FZZT brane. There's an incredibly interesting story about that having to do with, and also with 2D black holes, but that goes beyond this talk.
I see. So there is not really a direct analog of the FZZT brane in the matrix model as of now.
Okay. So what I meant to say is that if you want to add, you should think of FZZT brane as if you add FZZT brane to the background, you're changing the background, and there's a different matrix model.
Yes.
There's a different matrix model. As far as I know, we don't actually know the precise matrix model due to FZZT brane. When you just add FZZT brane, there's some proposal, but it has not been made completely precise. But we do understand a limit, which is you let this FZZT brane retract to the weak coupling region. So if it is very far away and have open string with very high energy comes to the bulk, this we do understand the matrix model. In fact, this was first conjectured by Juan Maldacena to be due to the non-single sector of the same matrix quantum mechanics. And we had some recent non-trivial evidence for that at the level of perturbation theory.
And this FZZT brane is stable, or can it decay like with tachyon condensations, things like this?
They're stable. So there are unstable ones. If they come in too far into the box, they can become unstable. But I was restricting myself to the stable one. So there's a 1% family of the stable amplitude brain.
Okay, thanks a lot.
Thank you.
Okay. Okay. Can you comment on this prior some?
Oh yes. I'm not sure if I heard the entire question. I think the question was about the Borel summability. So I said that. Let me go back. Where was it? Oh yeah. So I commented that these perturbative expansion of sequence string theory is Borel summable. So if you believe the duality with the matrix model, which has been checked explicitly up to one loop order with directed and worldsheet, then you can just take the matrix model answer and inspect it. And the matrix model answer is known exactly to all order and including the perturbative effects in this particular proposal for the number completion. And one can prove that it's Borel summable. The way that this proof works is actually very simple. It makes use of some very old mathematical theorem, proving I think in the 1920s, that tells you that if a function has certain property that's relatively easy to check in this case, then it is equal to its Borel summation of its asymptotic series. So that's how we know that the series is Borel summable, and that's how we produce this expansion. So in fact, if the perturbative series has not been Borel summable, you would expect some ambiguity in what you may mean by the instant correction. You have to say what you mean by that, because depending on how you resum the perturbative series, you have to maybe change what you mean by the instant correction on top of it. But in this case, there's no such ambiguity. But as I said, I don't expect this to be completely general. So in type 2B superstring theory, we know that some instant effects which has some net charge are unambiguous because they do not mix with the perturbation theory. But then you have anti-instant contribution, then you have to worry whether it's really well defined.
Okay, I think now it's time for a coffee break. And so we are going to reconvene in 10 minutes from now. Okay, so I think we can resume our session. So our next speaker is Ashoke Sen, and is going to tell us about complex to divergent amplitudes in two-dimensional string theory. Okay, divergent to complex amplitudes, sorry, in two-dimensional string theory. So,
okay, can you see my slide?
I can see your slides, yes.
Full screen?
Yes, they are full screen now, yes.
Okay, okay, thank you. So I'll thank the organizers, in particular Nathan, for inviting me to give this talk. So my talk today will be on divergent to complex amplitudes in two-dimensional string theory. So what I'll do, the plan is to divide the talk into two parts. In the first part, I'll introduce the problem, and in the second part, I'll discuss the solution. Okay. And my job is made easy by the beautiful talk by C that he gave before me. Okay. So my first few slides will be essentially a review of what he has already told you, but it's probably not bad to hear it again. So let me introduce you to the problem that we want to address in this talk. So in this paper, Balthazar, Rodriguez, and In computed the D-instanton induced scattering amplitude in two-dimensional string theory. Okay, this is what he described in his talk. So the worldsheet theory here is the time coordinate and the C equal to 25 Liouville theory. Okay, so it's really a critical string theory, total central charge adds up to 26. But in this theory, the closed string tachyons are really massless particles. So what they did is to analyze the scattering amplitudes of closed string tachyons, okay, induced by single D-instanton. Okay, in fact, they proceeded later to also do multiple D-instantons, but I'll focus on single D-instanton amplitudes. So after computing the scattering amplitudes from the worldsheet theory, they compared this with the result that they obtained from a dual matrix model description. So let me give a brief review of the results. So for one-to-one scattering, that means one closed string tachyon scattering into one closed string tachyon, the leading contribution comes from the product of two disk one-point functions. These you saw in C's talk before me. And the result for this is given by this expression over here. So I'm using a convention that's mostly identical to what C used, except that for me, the energies will be counted as all ingoing. So for example, an all outgoing. So an incoming tachyon will be counted to have energy minus omega 1. Okay. So in this form, that momentum energy conserving delta function takes the form of delta omega 1 plus omega 2 instead of delta omega 1 minus omega 2 that he was using. But otherwise, this formula is identical to what he showed. N is an overall normalization constant, about which I'll say a few more things later. At the next order, there are three contributions. First, we have the two-point function on the disk, which is shown here. And they computed this, and the result that they found is given here. So this part, as you can see, is the same as what we had in the previous slide. The new thing here is this function f, which is a function of the energies. This they computed by computing this two-point function. So this is a known function, and we'll see explicit form of this function in a few slides. Then you have the product of this one-point function and annulus one-point function. So it's this diagram plus the exchange diagram, 1 and 2 exchanged. Again, they computed this explicitly, and they wrote the formula in this form. And as you can see, this part is the same factor that we had earlier, and you have these two functions g omega 1 plus g omega 2. So g omega essentially refers to this annulus one-point function normalized by the disk one-point function. Okay, that's why you have the product of two disk one-point functions factored out, and then you have the sum over g omega 1 and g omega 2. And this again is a known function that will be described in a few slides. The final contribution came from the product of two disk one-point functions and the 0-point function on a surface of Euler number -1. In fact, there are two surfaces of this kind. It's a disk. You can either have a disk with two holes or a torus with one hole. Okay, here I have only shown one disk with two holes, but you should also add to this the contribution from torus with one hole. And this contribution again has a structure like this. So this is the product of two disk one-point functions that you have already seen. And this contribution from this diagram is what I'm calling C, this plus the torus with one hole. That's just a constant. So this can in principle be computed, okay, but it has not been computed. Okay, so I'll leave the constant as it is. So then they compared this string theory result with the matrix model results for imaginary values of the energies. And then they found remarkable agreement. They had to do this evaluation on the string theory side numerically. But after they did that, they found remarkable agreement with the matrix model results. So in doing this comparison, there are divergences in the open string channel, and this forced them to express the result in terms of two unknown constants, which had to be adjusted to fit the data. And these and more constants can in fact be fixed from first principles using insights from string field theory. But this was discussed in the last week's lectures, and we'll not say anything more about this in this talk. Okay. But all ambiguities in principle can be fixed, okay, associated with divergences in the open string channel. Now, the same functions, f, g, and c, can also be used to compute 1 to n amplitude. So 1 to n means one tachyon scattering into n closed string tachyons. And the reason that the same functions can be used to compute this amplitude is because the building blocks are the same. Okay? You have basically a product of multiple disk one-point functions, okay? Because that's the dominant contribution. And then you can take the product of that either with a disk two-point function or an annulus one-point function, or just a vacuum amplitude on a surface of Euler character 1. So using this simple worldsheet picture, you can get the string theory result to first subleading order, and that's given here. Okay. This factor again is similar to what we saw, except that now there are multiple products because there are multiple disk one-point functions. And then you have this factor over here. This one is the leading term, okay. And here you see the order TS corrections. These are from pairs of two-point functions on the disk. These are from one-point function on the annulus, and this is from the vacuum amplitude on surface of Euler character -1, or a number -1. Now here for comparison, I have given the matrix model result for the same amplitude, which looks the same, except the matrix model also tells you what the overall normalization is. Okay, that's -1 over 8 pi squared. So from now on, we'll set this n from string theory also as -1 over 8 pi squared, even though we don't have first principle derivation of this as yet, and carry out the comparison. So from these two formulae, we see that it's easy to identify this set of functions, this combination here, with the matrix model answer, which is given here. And this is what I'll write out more explicitly in the next slide. So here is a statement: the equality of string theory and matrix model results require that this combination of functions that you compute from the worldsheet description is given by this combination that you compute from the matrix model. Now this, of course, is an elementary function, but this is not so elementary. This involves complicated integrals. And here I have written down explicitly the string theory results for these functions f and g. So the details are not too important. Okay, in the small prints, I have explained the various things. So f, for example, involves the disk two-point function of Liouville primaries, okay, which are here. G involves Dirac and Deta function because it's really a one loop open string amplitude. So it involves Dirac and Deta function. It involves the odd Jacobi theta function. And here is the one-point function of Liouville primary on the annulus. Now the important point here is that the integrands of f and g are purely real. Even though there are factors of I you see here, these functions are in fact real for imaginary argument. Right? Dirac and Deta function, for example, is real for imaginary arguments. So is this one. And similarly here, even though you see I here, this is an upper half plane amplitude. And by the standard trick of evaluating correlation function in the upper half plane, the doubling trick, you also have to insert the images in the -I and -Iy. That makes this integrand real. So here you have a puzzle. So we have this identity. This is elementary. okay, but this is purely imaginary. On the left-hand side, we have functions f and g, which are manifestly real. Well, which looks manifestly real because the integrands are manifestly real. So one might ask, how can this relation hold? In fact, this problem is not new to two-dimensional string theory. This is a generic problem in worldsheet description of string amplitudes. Because worldsheet description of string amplitudes always gives a formally real amplitude. And in fact, what one finds is that whenever an amplitude is supposed to develop imaginary part, like for example in scattering amplitude, if you are above the threshold, you expect imaginary part of the result. But what you find instead is that the worldsheet expression, instead of giving finite answer, it diverges. And then one invokes the fact that then you have to define the worldsheet result by analytic continuation, and that presumably will generate the appropriate imaginary part, which will match the expected result. Okay, so this has been studied by many authors over many years. So what I'll describe today is the string field theory version of how to deal with this problem. Now, fortunately, these functions f and g that I showed in the previous slide, they also diverge. Okay, and the relevant divergences here, these are closed string channel divergences. So they diverge as y goes to 1, and then they diverge as t goes to 0. These are different from the divergences in the open string channel that we discussed last week. So these do diverge from y goes to 1 and t goes to 0 regions. And so the hope is that somehow, once you analytically continue properly, you should generate the correct imaginary parts. Okay, and we'll see how to do this. So this more or less finishes the statement of the problem. Now I'll describe the solution. So the strategy is to understand the origin of the divergences using closed string field theory and rectify them. Now we'll see that we will not need to know too much about closed string field theory except a few details. So the main point, okay, which is also common to open string field theory, is that the worldsheet divergences that we see in string theory always arise from the perspective of string field theory from the Schwinger parameter representation of the propagator. So if you have a Feynman propagator of this kind, in the Schwinger representation, you write it as an integral of this kind, which you can also write as an integral over q. And it's the q's which become the worldsheet variables like y that you saw in the previous slide after appropriate redefinition, and then the integral will diverge if k square plus m square is non-positive. Okay, we can clearly see that this is divergent when k square plus m square is less than or equal to 0, even though for negative values of k square plus m square, this side is perfectly fine. So what we will do is to try to use the replacement rule. Whenever you encounter a divergent factors like this, we'll use the replacement rule that a integral of this kind will replace by alpha minus I epsilon inverse. This minus I epsilon is included because the propagator we know from field theory is that it's actually k square plus m square minus I epsilon inverse. That comes from the standard weak rotation, and that's a procedure that one also uses in string field theory. So you should keep this in mind that this is the replacement rule we'll use. So for negative alpha, okay, when this is divergent, we'll simply replace it by the right hand side. Now the other advantage of this replacement rule is that for generic alpha, this rule is not sensitive to parameter redefinition. So for example, if we define a new variable, q tilde, which is some function of q with an expansion around q equal to 0, and this is the inverse function, and then if we re-express the integral in terms of q tilde, and then apply the replacement rule by simply expanding the integrand as a function as an expansion, series expansion in q tilde, one finds that one gets the same result. So the precise choice of the variable q is not important for making sense of this integral. So this replacement rule stated in terms of q or q tilde gives the same result. So with this, we are ready to tackle the divergent parts. Okay, at least the divergent part of f, okay, which is easier. So here I have written down the divergent part of f. Okay, I wrote down the full expression for f in a few slides ago, but the divergent part, here again by divergent I mean the divergent from the closed string channel, okay, which comes in the y goes to 1 limit, is given by this. So this c is the 3-point function of Liouville primaries that carries Liouville momentum p1, p2, p3. And you see that this is indeed divergent when this quantity is negative. So when 2p square is less than omega 1 plus omega 2 square by 2, this integral diverges. So now we have learned the rule. We simply replace, we call q equal to 1 minus y, just rename the variables, q equal to 1 minus y, and then replace the integral in terms of q first. And then you use a replacement rule that whenever you have dq q to the minus 1 plus alpha, we replace it by 1 over alpha minus I epsilon. So this is what you would get if you had been computing this amplitude in string field theory instead of using worldsheet theory. So now we substitute this here. So you have made sense of this integral. So the divergent integral, which was in f, is now replaced by this integral over here. And you can see that this is indeed a finite integral. Okay, there is no divergence in this integral, but it has both real and imaginary parts because we have this I epsilon over here. And whenever omega 1 plus omega 2 is 2p, that's the pole. So you can replace this by the principal value plus I pi times delta of this. So the I pi delta of this gives the imaginary part and the principal value gives the real part. So this way you can make sense of the divergent part of f. Now let's try to make sense of the divergent part of g, which is a little more tricky. So here is the expression for the divergent part of g. Again, I wrote down the complicated expression earlier. This is an approximation to that expression near the divergent region. So here this T1 and T2 are related to these variables T and X that we introduced earlier by this relation, and indeed we see that the divergence which comes at large T1 and T2 actually corresponds to small t. Okay, T goes to 0 limit corresponds to large T1 and T2, and you can easily convince yourself that this integral diverges at large T1 T2 for omega larger than 2p1 plus p2. So that's why I have cut off these integrals at upper limit omega, because there is really no divergence when p1 is larger than omega or p2 is larger than omega. So we need 2p1 plus p2 to be less than omega for this integral to diverge. So this you can see simply by taking appropriate limits. Okay, so now let's look at the origin of this divergence. So g, remember, was a one-point function on the annulus. Now one-point function on the annulus, from the closed string field theory perspective, the divergence comes when the incoming closed string splits into a pair of closed strings, and then each closed string joins onto a disk. So this is the limit in which the annulus becomes like a long cylinder. The annulus becomes like a long cylinder, and the closed string just joins into the annulus in the cylinder in the middle. So we expect that this is the kind of string field theory diagram that is responsible for what we see as a divergence in G, because we have used the wrong use of Schwinger parameterization for these propagators. So if you had a diagram like this, we would get an integral of the following form. So here omega tilde is arbitrary because we have momentum conservation here. So total energy, we have energy conservation at this vortex. So total energy of course adds up to omega, but omega tilde has to be integrated over. So let's imagine that we have an integral of over d omega tilde, and then the two propagators. Now normally we write the propagator as minus e square plus p square, but I am using the same notation that BRY used. Okay, where the on-shell condition is really omega equal to 2p1. That's why this minus 1 quarter. Okay, but otherwise this is just a normal scalar propagator. So let's suppose that you have an integral like this, okay, which is what you would get from a string field theory diagram of this type. So this has poles, of course, but it can be evaluated to give a finite integral, okay, because you can just deform the contour diagram from the poles and evaluate it. And later on, we will give an explicit expression for this. So here is the integral again. Now suppose we try to do Schwinger parameter representation of this, which you shouldn't do because you have a negative argument. We see that this is negative, this can become negative. So we shouldn't use Schwinger parameter representation, but of course worldsheet theory uses Schwinger parameter representation. So let's do it anyway. So we represent both these propagators by Schwinger parameter representation. We get an integral like this. And now we weak rotate omega tilde to IU and carry out the U integral using Gaussian integration. And we get an integral like this. And this integral, in fact, is what we had seen earlier, 2 slides ago. It's exactly an integral of this form. So what this is saying is that when you have a divergent integral of this kind, it actually represents an integral of this kind, which is perfectly finite. But here it looks divergent because you have made wrong use of Schwinger parameterization. So the idea now is that in order to make sense of these integrals, we simply replace worldsheet expressions of this kind by the top expression, which has no divergence. And again, like in the previous case, I should say this procedure is robust in the sense that it does not change under reparametrization of the TIs. Okay, we start with an expression like this, we replace it by this. Now you change variables Ti to some function of Ti, okay, which has some expansion near t equal to infinity. Okay. And in terms of the new variables, you have a new integral, and again we use the replacement rule over on the new integral. The result that you will get will be exactly identical. Okay. So the detailed choice of whether, so the detailed procedure of identifying T1 and T2 with the string field theory variables is not important here. Thank you. Okay, so this is then what we'll use. We'll replace divergent integrals of this kind by a finite integral of this kind. So let's see what we get by doing this. You can also think of it in another way, that these two integrals actually agree for sufficiently small omega when this dominates. So these two integrals are same analytic functions of omega for sufficiently small omega. Now this is well defined even for when omega exceeds that limit, P1 plus P2, 2P1 plus P2. This one is not well defined. So then this must be the analytic continuation of this. Okay, because this is an analytic function over the full omega plane. Okay, so this now tells us what the divergent part of g omega should be. So here we had, this is the expression that we had, and now the idea is that we will simply replace this divergent integral by a finite integral of this kind. This one now is perfectly finite, except that it has both finite real and imaginary parts. And I'll try to make this more explicit in the next slide. So the idea is that we have this omega tilde integral, which is along the real axis, and we will try to simplify this by a weak rotation. So if you look at the pole positions in the omega tilde plane, here are the pole positions. So omega tilde integral is running along this. So the idea is that we will rotate this integral to be along the imaginary axis, and in that process we just pick up the pole, the residue at this pole. Okay, so you have finally an integral about the imaginary axis. So we'll replace omega by IU, or omega tilde by IU. So that's the U integral on the imaginary axis, and then you have the residue at this point. And here in the small print, I have given those two expressions. So this is the integral along the imaginary axis. This, in fact, one can check is completely real, even though it has an I. There is an U goes to this, changing I to minus I can be undone by U goes to minus I U transformation. Okay, because this integral is symmetric under U goes to minus U. Okay, so this is real. And this part looks real except for this minus I epsilon. Okay. So this has an imaginary piece. So the way to deal with this integral is that we just replace this by the principal value plus I pi times delta of this, and that gives the imaginary part and real part, both of which are finite. So this procedure then gives manifestly finite f and g. Furthermore, from these expressions, one can get analytic expressions for the imaginary parts of f and g, because imaginary parts are really simple, because as you can see, the imaginary parts are proportional to delta functions, so most of the integrals are gone, and in g one integral is left over, but that you can easily do, and this is what we find for imaginary parts of f and g. And what one finds furthermore, that this exactly reproduces the matrix model result for 1 to n tachyon scattering amplitude, which is purely imaginary. So when you compute the imaginary part of the right hand of the string theory answer using these, you match exactly the matrix model. Here this is a comment in passing that if we had just wanted the imaginary part without caring about the real parts, then we could also get this using Katkowski rules of string field theory. So the imaginary parts out of the way, we can now state the agreement between the matrix model and string theory results by this relation. The real part of the amplitude must vanish, but this should happen not for all omegas, because you know this correspondence between matrix model and string theory results only in the special case of 1 to n scattering amplitude. So one of them has to be negative, the incoming one, that's omega n plus 1. All the others should be positive. So what we want for the agreement between string theory and matrix model results is an identity of this kind. These are on the finite functions, and so in principle this can now be verified numerically for all real omega i's. And in the process of verifying this, we'll fix all the 4 constants that I discussed last week that are apparently ambiguous on the string theory side, but which can also in principle be fixed from open string field theory. Okay, so I think that's it. Thank you.
Thanks a lot, Ashok, for your very nice talk. And so if there are questions, please just open up the mic and speak.
I have a question, Ashok. Is there any way to concept, or is there any way you know that you cannot construct a string theory that directly gives these finite integrals instead of giving the ones that that you have to replace?
Well, see, string field theory will always give these finite integrals because they will do with propagators, not with the worldsheet integrals, right? So if you start with computing this amplitude from string field theory, you will always get finite results. But from the worldsheet perspective, I think you will get infinite results, because the worldsheet, directly worldsheet integrants are never imaginary, never complex, right? They are always real.
Yeah.
So if you want to produce an imaginary result from the worldsheet integral, right, the only way is that you will encounter some divergence, and then you have to analytically continue to produce the imaginary part.
I think we are not seeing Ashok's screen anymore for some reason.
Yeah, I think, should I put my screen
probably,
on?
Probably the next speaker has already shared his screen, but please, Ashok, I think if you share your screen, then we will see it again in case it is needed for some question.
Okay, yes.
It should just work like this, probably.
Okay.
Yeah, I'm not sure that I can share my screen. Okay, yeah, I think I can share if necessary, yes.
Yes, okay. Other questions?
Yes, I have a question. So this formula of f, omega I, omega j.
Yes.
So this, in the case of 2 dimension, is like a Yang-Yang functional. So the query point gives a Betz ansatz.
This is what functional?
Yang-Yang functional for 2 dimension. So the query point gives a Betz ansatz. So is this probably this relate to the integrability?
Well, from the worldsheet perspective, they are pretty complicated functions, right? I mean, if you go back to the expressions for f and g.
Well, it's 2 dimension. Yes, it's just green function.
Yeah, this is Liouville correlator, right? In fact, I think in the BRY analysis, I mean, this correlation function itself, I mean, this as well as this, were calculated by conformal block decomposition, right? I mean, there's no compact formula for these. Right? So I think it's quite hard to deal with these directly, but I agree that eventually, since f and g satisfies this nice property, right, there may be a better way to prove this directly. I should also say that these have the divergences, right, from the open string channel as well. And those have to be fixed by other considerations from open string field theory. Okay? And it's only after you fix all those constants that you should satisfy the final identity that I showed you. The 0 that we saw here. Right? I mean, this F real and G real contains all the other constants that have to be fixed by open string field theory.
Oh, okay, thank you.
Are there other questions? So I have a quick question. So can you do this trick also for open strings? I guess so, right?
Yes, you can. I mean, for D-instantons, of course, you cannot do it because there are no momentum.
Right, right. Yeah.
Yeah, but for any open strings on general D-planes, you can certainly do this. As long as you have a momentum and you are trying to do analytic continuation, I think you can always do this.
So this is in a sense equivalent to analytic continuation in momenta, or?
Yes, exactly. Because the point is, I mean, the reason that you can be completely sure that this replacement rule is true, right? This is a valid procedure, is that these two functions agree with each other for small omega. So as an analytic function, they are identical, right? Now this is analytic also for large omega. This one is divergent, right? So you know that this is the analytic continuation of this one.
I see. Thanks.
It's just that this gives an explicit analytic formula for the analytic continuation, which is finite.
Okay, so if there are no other questions, we can thank again Ashoke. Remember, there is a discussion session going on after, so we can continue our discussions. But now it's time to introduce the next speaker, Albert Schwarz from University of California in Davis, who is going to tell us about scattering matrix and inclusive scattering matrix in quantum field theory and string field theory. So please. We can see your screen already, so please go ahead. Thank you. I think we cannot hear your voice. You are muted. So let's see. Maybe I am not able to unmute you, unfortunately. Perhaps Nathan, can you unmute Albert?
Yes.
Okay.
Okay.
Okay. So no. Now you're muted again. Okay, now you can talk.
Yeah.
Thank you.
Okay. It is nice to participate in the workshop on string field theory, and I would like to stress that I really did not work in this field. So basically what the results that I will explain, they are about quantum field theory. But they are applicable to string field theory. And I think that it would be very interesting to get real results in this direction, because what I will be talking about are more conjectures than results. So let me talk first about the general results that I have. First of all, there are old results, but are believed that are not really well known, is that to construct scattering matrix, you really do not need local quantum field theory. What do you need? An algebra is asymptotic commutativity. I will later explain what does it mean more precisely. So I'm quoting some papers, and the first of them is about the stuff, mostly string theory, mostly field theory, but also what is emphasized there, that it can be applied to string field theory. Newer papers are about the notion of what I'm calling
inclusive scattering matrix. And the statement is that really you can apply the scattering theory also to scattering of quasi-particles, but only in the case when you consider inclusive cross-section. And you should have, and the scattering matrix also should be modified. I'm calling this inclusive scattering matrix. In this picture, one should use generalized Green functions that also should be will be defined in a moment. What I would like to say also, that all the stuff arises very naturally if you formulate the quantum field theory in terms of positive functionals on Weyl-Clifford algebra that I called L functionals. And the analog of scattering matrix in this formalism is precisely inclusive scattering matrix. And the analog of Green functions are generalized Green functions that I already mentioned. And you can get a diagram technique for them. And this diagram technique coincides with diagrams of Keldysh formalism and thermofield dynamics and statistical physics. In preparation, I have a paper with Andrei Mikhailov, where I represent the string theory in the formalism of L functionals. And also I would like to say that all of the stuff is exposed in my book about mathematical foundations of quantum field theory that appeared very recently, a month ago in World Scientific. This is mostly an old book, translation of old book. But the quantum field theory is developed there without the assumption of locality. And therefore it is really appropriate to string field theory. And and I added a chapter that contains in particular these new results about inclusive scattering matrix. So I used some terms here that should be defined. And let me do this right now. First of all, the notion of inclusive cross-sections, I believe, pretty well known. But really, there is a definition here. Basically, the inclusive cross-section of some process is a sum of cross-section of processes where you have also not only the particles that you are interested in at the end, but also some particles that you do not observe or do not want to take into account. And then you are summing over all the stuff that you do not want to look at. So the notion of inclusive cross-section So usually, if the usual cross-section comes from scattering matrix, or better to say from matrix elements of scattering matrix squared. But I introduce a notion of inclusive scattering matrix that is related to inclusive cross-sections. But here you should not take any squares. Then I talked about quasi-particles. What is quasi-particle? I define quasi-particle, I define as elementary excitation of some translation invariant stationary state. This stationary state could be a ground state. Then you talk about particles. It can be a thermal state, equilibrium state. Then we talk about thermal quasi-particles. But what I would like to stress that when you consider scattering of quasi-particles, then only inclusive cross-sections make sense. And so therefore, I believe that in statistical physics, you are forced to use the notion of inclusive scattering matrix. So my starting point is an algebraic approach to quantum field theory. This means that I am starting with associative algebra equipped with anti-linear involution. A state is a positive linear functional on this algebra, and positivity is reflected by the requirement that this functional is non-negative on every element of the form A star A. The state is called normalized as omega of 1 is equal to 1. And the time evolution is given by one parameter family of automorphism of algebra, and the symmetries are automorphism of the algebra that commutes with time evolution. And to have a notion of space-time and the notion of scattering matrix, you need a group, an abelian group of space-time translations acting on A. So basically, you do not need a notion of space. The space you don't, but basically, what's the only things that you need? You need a group of translations that are called space-time translations. And this is sufficient to define everything that we need in physics. After that, we consider some translation invariant stationary state. This is very well defined because the group of translations that acts on the algebra can be considered also the translation of states. And you can define a notion of asymptotic commutativity. The asymptotic commutativity means that if you take an element of algebra and shift it in spatial direction, then the commutator with any other element of algebra is small as x tends to infinity. So basically, the notion of small can be defined in different ways, and I do not want to go to the subtleties now. But of course, all the stuff can be made rigorous. So in the standard version of quantum mechanics is the algebra of operators in Hilbert space, and positive functionals are in one-to-one correspondence with density matrices. So now one can develop a scattering theory that generalizes the scattering theory developed many years ago by Haag and Ruel in relativistic theory. And what can you do if the standard scattering matrix makes sense? It can be represented in terms of green functions. Better to say, in terms of green functions on shell. And the representation is given by the famous LSZ formula. But also, you can define generalized green functions corresponding to some translation invariant stationary state omega by the formula which is written here. You have this functional, and you should omega that describes the state. And you should calculate it on a product m by n, when n is a chronological product of some operators, of some elements of algebra, better to say. Bi are elements of algebra. And M stands for anti-chronological product, where times are increasing. So you can, this is a definition of generalized green function. And the main statement is that the inclusive scattering matrix and inclusive cross sections can be expressed in terms of these generalized green functions on shell as an LSZ formula. So then the next question is how to calculate these generalized green functions. And here one can apply the notion of L functional that I mentioned. So what is an L functional? As I said, this is a positive functional on Weil algebra or on Clifford algebra. And it is related to density matrices by the formula which is written here, where A plus and A are generators of Weil or Clifford algebra. And for these L functionals, you can write down equations of motion, if you know the equations of motion for density matrix. But what is important that the Weil algebra has many representations we are usually working in Fock representation of Weil algebra or threefold algebra. However, there are many other representations, and it is necessary to use other representations. So, and the statement is, if the Fock space is too narrow for you, and this happens all the time. For example, the equilibrium states are never in Fock space, and the dressed vacuum, the physical vacuum, is never in Fock space. Still, you can use L functionals where all representations of Weil algebra are represented. And in the language of L functionals, the analog of green functions are precisely these generalized green functions that I talked about. And applying the standard diagram technique to L functionals, you get this diagram technique for generalized green functions and for inclusive scattering metrics. So I definitely do not have time to talk about the stuff in more detail, but this is a workshop on string field theory. I would like to talk about possible applications of these techniques to string theory. And here, the situation is very clear in light cone formalism. Let me remind to you that in light cone formalism, the Poincaré group, and in particular, the group of translations, acts on single string space. And this action can be extended to corresponding Fock space. I consider critical closed string. And you can define an asymptotically commutative algebra acting on this Fock space as an algebra generated by creation and annihilation operators. And you can calculate the corresponding scattering matrix using the technique that I have explained, but it is trivial. However, you can deform the action of Poincaré group on the Fock space, taking into account the string interaction. And I give references where this is done. And this is, can be called a Hamiltonian version of light cone string field theory. And it is, in this version, you can define the scattering matrix and inclusive scattering matrix using the techniques that I have explained. You have the asymptotic commutativity that I need, and it seems that it's easy to prove that this definition of scattering matrix in terms of LSZ formula, it's concise with standard definition of scattering metric in string field theory, with one difference, that LSZ formula takes into account the mass renormalization. So, and as usual, generalized green function should give inclusive cross-sections. But what's the situation with covariant approach to string field theory? So in BRST formalism, you can replace the single string space by homotopy equivalent differential module. Differential is mathematical words for BRST operator. So in this approach, you base for simplicity of action of Poincare group by introduction of BRST differential. However, it is not clear how to construct this BRST operator in interacting string field theory. Probably one can give a mathematical proof for existence of such a necessary deformation using what's called homological perturbation lemma or its generalization. But there is another way that can be suggested. And again, I cannot go in this direction very far. This is simply, you can start with Lagrangian approach with string field theory. This is very well developed for covariant string field theory, and go to Hamiltonian approach. And the reasonable idea of how to do this is to apply what is called covariant symplectic formalism. For open string fields, for open superstring, this was suggested by Witten, as I was informed by Barton. But it seems that also in this, even in this case, you cannot really finish Witten's program, as was shown by Gross and Erler. That's thanks Ted for informing me about this. So it seems still that what Witten has chosen was a wrong way to apply this covariant symplectic formalism. And here, do I have a couple of minutes?
You're now in the question time, so, but you can continue talking and then.
Mm-hmm. Yeah, okay, so let's say I needed 1 minute. So there's what can one do is to describe this covariant symplectic formalism in the form that it can be applied in the case of infinite dimensional phase space. And I make a suggestion how to consider. I define the notion of space-like hyperfuse surface in this case as a surface that you should fix the string field, which is an solution of equation of motion, if you know it in small neighborhood of space-like hypersurface. And I give a conjecture how can one construct of such hypersurface in the covariant string field theory. I wanted to talk also something about geometric approach to quantum theory, but definitely I have no time for this. That's it.
Okay, so thanks a lot for the very nice talk. Are there questions? So just simply unmute yourself and ask.
So if there are no questions, I would like to say a couple of words about geometric approach to quantum theory. So really, what did I develop is a geometric approach to quantum theory, where the starting point is the set of states. So it's, in this approach, you can prove what is called the coherence and derive formulas for probabilities from the first principles without taking them as axioms. And for Jordan algebras, you can apply this geometric approach, and probably this could be very useful for consideration of superstring, because there is a suggestion that is partially successful, let me say, by Foot and Joshua, that superstring theory can be formulated in terms of what is called exceptional Jordan algebra. There is a unique Jordan algebra that cannot be obtained from associative algebras. The conjecture by Foot and Joshua is that superstring is closely related to this algebra.
Okay, so we can thank Albert Schwarz for his very interesting contribution to this conference. And so now the official talks are over, and we enter in the informal discussion. So essentially now I think that perhaps Nathan can stop the recording. That was somehow the idea, and then I mean this